Assalamu alaikum everyone. Welcome to first blockchain security workshop being conducted by Information Technology University Blockchain Security Lab. So this initiative is funded by National Center for Cybersecurity, and this is our second day in this workshop. In first day, we have learned about the basics of blockchain and how the system works. So we were being joined by our respected director and principal investigator, Dr. Muhammad Umar Janjua, and researchers here at Blockchain Security Lab. Today, we are fortunate enough to have Dr. Basit Shafiq with us as our first guest speaker. So Dr. Basit Shafiq is associate professor at LUMS, and he have been doing wonderful stuff in electrical engineering, data sciences, and similar domains. So I'll be inviting Dr. Basit Shafiq shortly. Meanwhile, I'll be reciting few Quranic verses to formally start the day. So Allah Rabbul Izzat say in Quran Kareem, he is teaching us a prayer that Rabbish Rahli Sadri wa Yassirli Amri Wahlul Uqdatam min Lisani Yafqahu Qawli. Sadaqallahu Azim. So with the formal start with the Quranic verses and the introduction of our respected speaker, Dr. Basit Shafiq, I would now like Dr. Basit Shafiq to take over the stage and talk to you guys about the things in blockchain security and related domains that we want to talk to you guys. Thank you very much, Dr. Basit Shafiq, for joining us. The floor is yours. Thank you.
Thank you for inviting me. This is a wonderful event. I was looking forward to it. I will, in today's presentation, let me first share my screen and let me know if you see my screen.
Yes, we can see it.
Okay, great. The topic that I want to discuss with you today is related to access control on blockchain. So we did some work on how blockchain can be used for management of access control for distributed applications. This work was published in a recent conference, NCCS 2020, and was presented there in December of 2020. The authors of this paper include my PhD student, Ahmed Akhtar, my collaborator, Jaideep Wadia at Rutgers University, Aisha Afzal, she's my former PhD student, Dr. Shafii Shamail, who is a professor at LUMS, and Professor Umar Rana, who's a professor at Cardiff University. So, as all of you know, that internet-centered this cloud computing and edge computing infrastructure has enabled development of internet-centered distributed applications. And these are autonomous, cooperative, and trustworthy applications, which are architected by using resources and services available on the cloud. Now, these resources and services may come from different organizational domains, and access to such resources is governed by the security and access control policies of respective domains. Traditionally, access control management systems were deployed in the resource owner domain, which results in significant overhead in terms of configuration, deployment, and management of this access control system, plus the hardware and deployment cost for these systems, as well as the human resources required to manage these systems. Another option is to outsource access control management and security to third parties, which has also been a widely adopted alternative that is being used nowadays. However, the trusted third party, again, the third party needs to be always available and must be trusted not to have any malicious behavior. Recently, blockchain has been considered as an alternate to the outsource environment, where the trust issue is resolved by providing, by supporting the auditability capability of blockchain. So blockchain provides this auditability. So trust issue in that sense can be resolved. And there are some recent papers that talk about how security and access control management can be done over the blockchain. So one recent paper by Mesa et al., which was published in Computers and Security in 2019, they presented a reference implementation of a blockchain-based access control system, which supports fine-grained access control policies. And these access control policies are specified in XACML, which is a de facto standard for access control, and support specification of very fine-grained access control policies. However, this solution works for a single resource owner, meaning that if you have a single resource or multiple resources, but these resources are managed and controlled by one single organization, and only one policy applies to that. In contrast, when distributed applications, as I said earlier, are composed of multiple resources and services which are governed by autonomous organizational domains. So these resources are subject to the security and access control policies of the owner domains. Moreover, the access control policies across these different organizations may be overlapping in the sense that they may have common clauses, common conditions. So if we consider that each resource owner evaluates and enforces its policy separately over the blockchain, then this will incur significant cost and computation overhead if there is significant overlap between these policies, because these policies will be repeatedly evaluated over the blockchain. This cost can be significantly reduced by avoiding a repetitive evaluation of these common clauses and conditions across policies. Now, I will explain this using an example. This slide shows a business process related to online course offering in a multi-university environment, where specifically in this example, we consider 3 universities: Rutgers University in US, LUMS in Pakistan, and Cardiff in UK. And these universities are collaborating to offer courses to the student of these participating 3 universities. So any student in any of these 3 universities can take a course which is offered by any instructor within these 3 universities. And this multi-university environment makes sense in today's environment, where all our courses are offered online. So here is an opportunity where students can take their favorite courses in any university they like. However, the underlying resources of these organizations are governed by their own security and access control policies, and they are autonomous. For example, this particular business process that you are seeing is related to assignment grading workflow, where TA first download the assignments from the learning management systems, in short, LMS systems of all 3 universities, and then transfer these assignments to either a codec to either a server at LUMS or another server. So there are two different servers with different policies. And then once the code is transferred to the server, an autograder is run. After running the autograder, the marks are uploaded to the, again, the learning management system or grading systems of all these three different universities. They have their own systems. And afterwards, a notification message is sent to the student about his or her grade. So if you look at this business process, you will see different systems and resources that are being accessed. And these access to these resources is governed by the security and access control policy of the owner university, the university that owns this resource. For example, if you look at the policy of this access control policy of download LUMS assignment, it states that a PhD student registered as an HEC scholar and having a CGPA of 3.5 can download assignment of his or her supervisor course from LUMS learning management system. Similarly, Rutgers assignment policy, Rutgers download assignment policy is a graduate student registered as HEC scholar can download assignments of his or her supervisor course. If you see over here, these policies are not exactly the same. However, there is a considerable overlap between these policies. For example, the PhD or graduate student has to be registered as an HEC scholar. So this part is common. Plus, he or she can download the assignment of his or her supervisor course. Now, so if you consider evaluation of these policies separately over the blockchain, then you have to repeatedly evaluate these conditions on the blockchain, which will incur more cost. So what we need is an efficient approach where we can combine these different policies and generate a composite access control policy that can be evaluated without repetitive evaluation of the underlying conditions. So in this work, what we have done is we have developed an approach for access control policy evaluation and enforcement over the blockchain while reducing the cost and computation overhead. And that part relates to avoiding repetitive evaluation of policies. In addition, we have developed an efficient mechanism for auditing access control decisions. So before I explain the proposed approach, let me first give you an overview of XSEML or access control policy. So we consider that access control policies are specified in XSEML, which is an XML standard for access control language. And in XSEML, the authorization of subjects over resources for some task is specified using authorization rules. So for example, here you have the authorization rule listed over here. In this authorization rule, you specify the requirements of the subjects with respect to different attributes, what attributes they must have, what would be the value of these attributes in order to check if they are authorized for a given access or not. Now, if you look at these rules are essentially composed of conditions which can be categorized as atomic condition, composite condition, permit or deny condition. So an atomic condition is a Boolean expression over a single attribute or a single predicate. Similarly, a composite condition is a Boolean expression in which multiple atomic or composite conditions are joined together by and or by conjunction or disjunction. A permit or deny condition is essentially a composite condition that specifies whether a subject is allowed to access, allowed or denied access to a particular resource with a given permission or not. So here is an example of an access control rule, uh, which is specified in a graph for simplicity. So XSCML, as it's an XML document, you know, XML documents can be represented as graphs. So here you have a policy representation for a rule which says that a PhD student who is a registered HEC scholar can download assignments from LUMS LMS for a course which is taught by his or her supervisor, and that student has a GPA greater than 3.5. Okay, now in this particular graph, all the conditions which are labeled with are labeled as red oval. These are atomic conditions. The green one is a composite condition, and the purple one is the permit condition. So coming back to our example, if you consider these different services or tasks of this business process, you have the policies of executing each of these service, which is specified by the respective organization domain. For example, download assignment from Rutgers, the policy for download assignment for Rutgers is given on this rectangular box, which is on the top left. This slide shows all the access control policies. And if you see these access control policies, there is a lot of overlap between the access control policies for different resources. So all the overlap in conditions is basically shown with the same color. For example, here you have is senior number here, and is senior is also shown over here. Also, this is repeated in other policies. So there's significant overlap between these policies. Now, what we can do is, in order to avoid that repeated evaluation, you can combine all these service provider policies into one single unified global access control policy, which does not have any repeated condition, which has only one in which you have a condition is represented only once. You do not have duplicate conditions. So you just simply take a union. So that's a global unified access control policy. So if you want to evaluate this policy on the blockchain, what you can do is you can encode this policy as a smart contract on the blockchain, and then you can execute this smart contract. However, this will not be optimal. For example, if you consider the same business process I showed you earlier, there are two branches. Either we can transfer the code, which is either we can transfer the assignments which are downloaded from all these three servers to a codec server at LUMS or to a different server. So also, we can notify students via SMS or via email. So overall, there are 4 execution paths for this business process. First one, which uses codec server and uses notify via SMS. The second one, again, codec server, notify via email, and so on. So if we consider one single global unified access control policy, then in a given execution of the business process, we will be evaluating the conditions for all the services in the business process, even though these services are not in the execution path. For example, if you consider the execution path shown with bold lines over here, so we use codec server and we use SMS notification service. We will be evaluating the entire policy, and we will be evaluating these red conditions as well, even though these conditions are related to the access control policies of the services, which are not executed. Okay. So that's the issue with the global unified access control policy. So what we need to do is we need to come up with some kind of optimal composite policy which results in minimum cost, and that avoids repeated or that avoids evaluation of those conditions that are not needed in the business process. So for this, what we do is we consider the unified global access control policy that I showed you earlier and partition that policies into multiple fragments. Each fragment includes one or more condition in the policy, and the union of these fragments is the same as the global unified policy. However, the sum of the cost of evaluating the smart contract for these fragments, so each fragment is encoded as a smart contract, and when you evaluate the total cost for the corresponding smart contract for any given access request, it gives you the minimum cost. So that's the problem that we are addressing in this work. Now, before I discuss the specific optimization problem and how is it formulated, I want to first give you the architecture of our proposed approach. So as I said, our proposed approach is designed for a cloud services environment in which the business process is hosted and executed by the cloud service provider. And the cloud service provider ensures that the access control policies of the underlying services are correctly enforced. So our proposed approach essentially includes 5 components. The composer is responsible for taking all these local access control policies of service providers and combining them into a global unified policy, and then later on generating a optimal composite access control policies, which is essentially fragmentation of the global unified policy. So each fragment is then translated into a smart contract. So that's the job of the translator. And then we have a deployment engine who deploys the smart contracts related to a policy fragment onto the blockchain. This deployment engine also registers the smart contract with the corresponding service providers so that they can audit if there is a need for auditing. The business process manager over here is responsible for checking the authorization of user request for executing the business process by invoking the corresponding smart contract on the blockchain. In addition, we have an adaptation engine which monitors the policies of these service providers for any changes. If there is any change, it then triggers recomposition of the global access control policy. So now I will focus more on this part, which is the policy composition, optimal policy composition, which, as I said earlier, is formulated as an optimization problem with the objective of minimizing the overall cost. And when we talk about cost, it's both the deployment cost for deploying the smart contract over the blockchain plus the evaluation cost. So we want to minimize the overall cost for access control management over blockchain. And our constraint is we do not want to violate any of the local access control policies of service providers. Now, since we are talking about the cost, so this equation gives you how we compute the overall cost. So for any given condition V, the total cost is given by this equation, which is a sum of the deployment cost for deploying the encoded smart contract for condition V over the blockchain. And this is a one-time cost. For each user request, you have to evaluate the policy. So EV here denotes the evaluation cost of the contract corresponding to the condition V. And this EV cost is incurred every time the policy or the condition V is evaluated. Now, we do not consider a single evaluation in this cost equation. We rather consider n evaluation. So we compute this cost for n evaluation, where n could be in 100 or in thousands. And PV is the probability that the condition V is evaluated during DP execution. So once we have this cost equation, then we can formulate this optimal policy composition problem as an integer programming problem, where the objective is to minimize this total cost for deployment and evaluation of access control policy, subject to this constraint, which is a condition coverage constraint that ensures that the policies, the local policies of service providers are not violated. And technically, this condition coverage is stated as for every subgraph which starts from an atomic condition and ends at a permit deny condition, the sum of XVs of all the conditions in that path should be greater than 1. I'm going to explain that in the next slide. Here, XV is an indicator variable which is either 0 or 1, which is that the condition V is selected or not. So if XV equals 0, the condition is not selected, it's not encoded in the smart contract. If XV is equal to 1, this means the condition is selected and encoded as a separate smart contract. So as I said earlier, the constraint ensures that the local policies are not violated. And so let's consider a constraint, the constraint here. So here, if you see the atomic condition V6, and you have a permit condition V0, permit all. What we do is we find a subgraph starting from this V6 and terminating at V0. So the nodes in that subgraph include V6, V13, V11, V8, V5, V7, V12, V0, and V9. And consequently, you would see this constraint that X6, which corresponds to V6 plus X5 plus X7 plus X8, X9 plus X0 is greater than 1. This constraint ensures that all the local policies are considered as constraint in our formulation in this optimization problem. Now, once we solve this, we run any integer programming solver and get a solution. So in the solution, some of the indicator variables XV would be 1, others would be 0. So XV equals 1 means the condition V and all its predecessor conditions are encoded as a single smart contract. For example, if you see over here, these rectangular boxes shows the smart contract that includes the condition which is selected, which is evaluated as 1, as well as all the predecessor conditions. Okay, this is a composite condition, therefore we need to include its predecessor conditions as well. So in this solution, we get how many smart? We get 9 smart contracts. Okay, some of these smart contracts have multiple conditions, which is basically a composite conditions and all its predecessor conditions. Some of these smart contract has only one condition. So this ensures that every atomic condition is covered in at least one smart contract. So if you look at this figure, you will see that all the atomic conditions which do not have any edge terminating at those conditions are included in at least some smart contract. There are some conditions which are for which we do not develop the smart contract, but these conditions can be evaluated by combining the evaluation of these different smart contracts. So that's how we come up with a composition policy. So this is our composite policy. Now, again, going back to our architecture, how we evaluate it. So the business process manager is responsible for evaluating the user request against the access control policies. And there, the access control policy, as we said earlier, is composed, can be composed of multiple fragments. Each fragment essentially is encoded as a smart contract. So this slide shows you the process for evaluating the access control request. So to execute a business process, the user first specifies the particular business process the user wants to execute and provide his or her credentials to the business process manager. The business process manager looks at these credentials and the user request, and then forwards these credentials to the respective attribute manager and invokes the relevant smart contract. Now, the attribute manager are responsible to provide the verified attribute values directly to the smart contract. To ensure that values of sensitive attributes are not leaked on the blockchain, the attribute managers can use public key, private key encryption, as well as digital signatures to ensure the values, the sensitive values are not leaked over the blockchain. So once the smart contract receives all the required attributes, the execution of these smart contracts begins, and then the authorizations are evaluated, and the results of these evaluations are sent to the business process manager. So the business process manager receives the results of these evaluations, and then the business process manager can combine the results it has received from these different smart contracts and determines the authorization over the user for a given request. Now, the business process manager, once it decides or it checks whether the authorization is allowed or not. If the authorization is allowed, the business process manager forwards the user request along with the transaction identifiers of the smart contract to the policy enforcement point of these service providers for providing access to the requested service to the user. The transaction identifiers of these smart contracts are also provided with the decisions so that these service providers can check whether their policies have been correctly enforced on the blockchain or not. So this ensures that the service providers can audit the decisions taken by the business process manager in terms of correctly enforcing their policies. A business process manager can cheat, but auditing prevents the business process manager to cheat. Now, what is cheating? A business process manager may cheat because every time a request is evaluated, there is a cost associated with it. So in order to save that cost, a business process manager has an incentive to cheat. But auditing prevents the business process manager to cheat. So in our proposed approach, the policy is evaluated online on the blockchain, which is low cost. But the auditing could incur a high cost if each service provider verifies all the service requests. So which means there is a lot of overhead with it. But this can be reduced because the service providers need not to check all the access requests. So to reduce this cost of auditing, we have proposed a game theoretic approach that models the interaction between the business process manager and service providers as an independent two-party game. Essentially, we formulated the problem in such a way that the computation which is needed to validate the policy is incentive compatible, that prevents a rational adversary to cheat. I think I am going, this may take some more time, so I'm going to skip the details of the auditing approach and go to the experimental evaluation. But as I said earlier, this work is published in ICDCS 2020. So you can read the paper, and then if you have any questions, we can discuss that. You can send me your questions. So I'll skip the auditing, the specific description of the auditing, except that this auditing approach reduces the overhead by making this computation of policy evaluation incentive compatible and ensures that the payoff to honest business process manager is greater than a cheating business process manager. So let me discuss the experimental evaluation results, and then I'll end the presentation and take some questions. So we evaluated our approach for computing the access control decisions over the blockchain. And for experimental evaluation, we considered three models. The first model, we considered that each service provider policy is modeled as a separate smart contract. The second one is we consider a single unified global access control policy. If it's deployed as a single smart contract, this whole policy, then what would be the cost? And finally, the third one, which is optimal composite policy, which is essentially, as I discussed earlier, is an optimal fragmentation of the global unified policy. And these experiments were run for 2,500 evaluations on Ethereum Ring-B testbed. This chart shows you the cost in Ether for these different policy models. So for separate policy model, you can see that the cost is much higher than the global mediated policy and the optimal policy. And optimal composite policy, if you see over here, is also lower than the global mediated policy. Now, this difference in cost is because of the degree of overlap between the conditions. So we also, in our next experiment, we also considered the effect of degree of overlap on the cost for policy evaluation. So the degree of overlap is computed using Jacquard index. The higher this Jacquard index, the more is the overlap between the policies. So if you see over here, if you have more overlap between policies, the difference in the cost between the global mediated policy and the separate policy, as well as global as well as the separate policy and optimal policy, it widens. Okay. Now, in terms of related work, as I said earlier, Mesa et al., whose paper was published in Computer and Security, they considered fine-grained access control policy evaluation over a blockchain. However, their work did not consider multi-domain security policies. There was also some earlier work done on access control management over blockchain, but that earlier work essentially considered exchange of access tokens as blockchain transactions between users. So user authorization is determined based on the possession of the token. So these tokens are created using public key, private key script and can only be unlocked by the user who has the access right over the resource. So the drawback of this token-based approach is that you cannot express fine-grained access control policies. The policy is evaluated on chain, but you cannot specify fine-grained access control policies. Moreover, this does not support multi-domain security policies. As opposed to this existing work, our proposed approach, it does support fine-grained access control policies. It evaluates the policies on the blockchain, but the decisions are taken by the business process manager by combining the evaluation result. However, the decision taken by the business process manager related to authorization can be audited by the service provider. And our approach is the first approach that support multi-domain security policies. So to conclude, we considered the problem of auditable access control management for distributed business processes. Our solution employs blockchain technology that minimizes the total cost for access control policy evaluation. And we also proposed an approach for efficient auditing that ensures that a rational adversary would not cheat. So I'll end here. If you have any questions, then I'll be happy to answer your questions.
Thank you very much, Dr. Basi Shafiq, for the wonderful session. I really hope that our participant got to know about blockchain interventions. So here we have a question by a participant named Hatim is asking, what does degree of overlap mean? So would you like to answer this?
So degree of overlap, as I said earlier, if the policies, the access control policies are defined as rules, and these rules are composed of conditions. And if these conditions overlap in different rules, then you end up evaluating these conditions multiple times. So every time you evaluate these conditions over the blockchain, you have to pay a cost. Okay, and that's the objective. We want to minimize this cost by avoiding repeated evaluation.
Right. So I hope this answers the question of Mr. Hatim. So here we are having no more questions. So I would really like to thank you on behalf of Blockchain Security Lab. And now we are also being joined by our next speaker, Dr. Khurram Bhatti, who is chairperson of Department of Computer Engineering here at Information Technology University. So Dr. Bhatti will be starting his talk very soon. So thank you, Dr. Basi Shafiq, for the wonderful session. We are hoping you to be there in talk of Dr. Bhatti as well, if you would like. And then after this session, dear participants, we will be having a short break. I would request you all to stay there during the break so your internet connection or the meeting room does not get disturbed. And we will be starting just after 15 minutes of the break. Right. So Dr. Khurram Bhatti, can you hear me and please confirm that you are also audible?
Yes, thank you very much, and wonderful talk, Basit Saab. I really enjoyed that. I hope you're around and we can have more chat around. So yeah, I mean, up to you. I'm available and I'm ready. So let me know when I can share my screen and start the presentation.
Sure, Dr. Khurram Bhatti, you can start right now, and we are really waiting to listen you.
Okay, so I'm going to share my slide. Please confirm if you can see. And for my own introduction, I'm going to open my camera for a few minutes so that people can see who I'm and who is speaking. So thank you very much once again. Please confirm if you can see my slides.
Yes, we can.
Okay, great. So thank you for the introduction. As I've been introduced already, so I don't need to go into that detail. I'm working with ITU for a couple of years. Well, actually more than couple, around 5 to 6 years now. And I'm working as an associate professor right now, and I'm also part of the blockchain lab as a co-PI. So within the blockchain lab, my primary focus is on the vulnerabilities assessment within the blockchain infrastructure. But today's talk is more around generic concepts and problem statement of hardware security and vulnerabilities in modern computing. I'll shortly let you know why I picked this topic and why I think it is important. So let's just start the presentation, and I'll just share with you what I plan to, talk today. So this is the, well, not very brief outline of my talk today. We are going to see a general concern around and general perception around the hardware security first, and we'll see what are the primary reasons behind that. And then we will see what vulnerabilities are actually coming out of uh, hardware, and particularly the performance centric design, how it contributed and how it actually created some more challenges for the community. And then I'll talk about some state of the art, some current threat model, and what kind of work is out there. And then we'll go into specifics of some of the attacks so that your audience can actually understand what we are talking about, how these information leakage attacks work. And I'll conclude my presentation with a discussion around open research problems and some future roadmap, how these problems can be dealt with. So I would like to give a disclaimer here that the presentation is more of a tutorial, because you've been hearing about blockchain a lot. Basit also spoke about this. Umar also talked about blockchain. So here you will have more of a tutorial uh, related to hardware security in general, because I see that there are a lot of students attending our workshop. So I would like them to, know a little more about what current challenges the community in hardware is facing when it comes to security. So let's move on. I will just turn off my video for in favor of bandwidth. So yeah. So as we already know this, that security is actually a shared concern across many application domains. When it comes to critical infrastructure, today we are concerned about almost everything, whether it is e-governance models, the banking sector, the communication systems, or basic infrastructure. So there is a general consensus, so we do not need to actually motivate or convince anyone about the security as a general shared concern. So let's just move on with how the security is being perceived at large. I've deliberately used this slide to actually discuss that the general perception about cybersecurity revolves around many concepts, many areas, all the way from digital forensics to network security. It talks almost about everything from governance to various aspects, whether it is cryptography. Uh, I'm sorry, my slides. Okay. Okay, so I was having some trouble with the movement of my slides. Anyway, so you see that almost everything is listed as one of the concerns in cybersecurity, but you hardly see hardware security aspects. You can see firmware security to some extent, but architectural level security is still not part of the larger perception when it comes to cybersecurity. So what I'm going to emphasize today is primarily the hardware perspective of security, and we are going to build with the problem statement first. So I believe you all have some basic background in computing, so you understand the computing stack. The hardware security problem primarily arises from the way we compute today. So if you see on my right hand side, it's a abstract representation of the computing stack where you have all the layers from all the way from application layer to physical layer. So the problem is that information leakage is possible even under safe software. Why is so? Because the underlying hardware at times is vulnerable because of its microarchitectural features, which are leaking information, and the state of your program execution may be revealing information that you do not intend to reveal. So even if you have encryption at the software level, even if you have very sound algorithms today, the problem is that the way your computing stack is arranged, it gives a certain privilege level to certain layers, and then some of those layers can be vulnerable to information leakage. For instance, if you talk about the hardware, this is just a very simple illustration of what we are talking about here. So whatever you do on the software layer, it has to go to some underlying hardware to be computed. So here we take, for example, an encryption operation being performed on a given microcontroller or a microprocessor, and a general flow would be that you have an input which has a plain text and a key, and that goes through your encryption operation computed on a particular hardware and generates a ciphertext at the output. So this is a basic operation that you perform in order to provide security at the software layer. I do not understand why my slides are problematic. Okay. Okay, so there is nothing wrong with that. So this is a general operation. You take an input, a plain text, apply the cryptographic operation, and generate a ciphertext at the output. What happens alongside is that while your hardware is computing or performing that operation, it generates certain sideline information. It definitely consumes certain power while doing operations. It uh, accesses data and instruction from your memories. So it doesn't, it does definitely have a certain access pattern, which is there. While doing so, I'm sorry, I mean, I don't know why my slides are moving on their own, but anyway. Okay, so you have a lot of side information which is there while the computation operation performs. So uh, while doing the encryption process, you have some acoustic profile, some electromagnetic radiation coming out of your hardware, and some power being consumed, and some access pattern is there for instructions and data. So all this information is there, and as long as you're not abusing that information, it is perfectly all right. However, modern security challenge when it comes to hardware actually demonstrates that this kind of information can be actually exploited in order to retrieve certain information. So there is nothing wrong with encryption as such. And we are going to put things in perspective with a small example from this paper of Seagate Technology, which actually shows that if you brute force an AES a 128-bit key, uh, presumably with all this computation power where you have every person on a planet with 10 computers and there are 7 billion people, obviously it's a bit um, not very recent information. So each of these computers, let's say, can perform 1 billion key combinations per second, and on average you can crack a particular combination with just 50% of the test. So with all these assumptions, you would still need almost this many years to brute force an AES 128-bit. Now, the problem is that with the side channel attacks exploiting the information that we just saw, which is leaking on the sidelines, it can actually break the very same 128-bit AES key in 28 milliseconds on an Intel i7 machine. Now, just imagine the kind of hardware attacks or hardware-based attacks where it comes down to breaking such a strong cryptographic key. All you need is to analyze the side channel information leaking from your hardware, and you can break the very same AES 128-bit key in less than, in a few milliseconds. So that's where the problem stands today, because side channel information or covert channel information is so powerful that it can, it has changed the way we perceive security at large today. So with this, I'm just going to elaborate quickly what are the information leakage channels that are, a bit of concern today. So there are two types of channels, primarily covert channels and side channels. So by definition, we can simply put them in a way that a covert channel is where any two processes communicate with each other that are not allowed to do so. So if you have two processes on the same machine and they are not allowed to communicate, but they find a channel to communicate, that would be called a covert channel. In the same way, a side channel is where one malicious process spies on another benign process and tries to steal or look into the operations of the other process. So we are going to see in a bit more detail how they look like. So for instance, a code channel could be any application installed on your laptop, and for instance, we have an offline image editor which we download from any app store, and we try to apply filters, and we believe that the app is localized, it is on your machine and disconnected from the internet on its own, unless you want to put something on, and you apply some filters and use your images, so it has access to your uh, photos library. On the other hand, which I mean, very common weather monitoring application, which is a very standard one on everybody's mobile these days. So that application is supposed to connect with the internet, obviously, for an updated temperature. And you assume that when I'm looking at the weather, it is my weather app, and when I'm applying the filters, it is my filters app. But if these two apps start communicating with each other and not allowed to do so in principle, you have uh, a covert channel established which actually has access to your photographs library through a weather monitoring app. So this kind of channel would be a covert channel. Similarly, if you look at the side channels, it would be a malicious process looking into the operations of a benign process, which is a normal operation that you are running on your machine. And it would, just like I explained earlier in an example, that you would have some operation, for instance, a cryptographic operation again shown here. But while you're doing the computation, it actually leaks certain information. And it could be all sorts of information, as we just discussed, that it could be hardware based information which is which is leaking on your hardware profile, um, and you need a proximity to measure that information. And it could be software based information which does not necessarily require proximity to your computing hardware. So it can be done at distance as well, like timing information, behavior of your memories, and access pattern of your information. These are some of the information that you do not need necessarily to be close to your computing hardware to measure. Now, having said that, we have to see that why is so that the hardware is actually so leaky. Well, the reason is actually stemming from the fact that over the last 4 to 5 decades, if you have an understanding of computer architecture, this is one of the most famous illustrations that you must have come across. That the computing architecture had a renaissance period where for straight 17 to 20 years, the computing has been very, very performance centric, and it had actually achieved a lot of performance, roughly 52% of performance increase per year. So when the design was primarily performance centric, security was always a second thought. So whatever was designed in that period, it was with the sole objective of giving you better performance when it comes to architecture. Now, just to have a look, this performance centric approach actually resulted into a lot of new innovative techniques. So, if you have taken a basic course on computer architectures, you might have come across most of these performance optimizations, where you have shared memory architecture, you have caching mechanisms, how cache memories work. Then you must have come across pipelining, how it works, so how instruction level parallelism can actually improve performance, how out of order and speculative execution can enhance your performance when it comes to conditional code, and so on and so forth. And then you have all the layers, all these computing layers have had, performance optimizations. Their new tools and techniques keep on appearing from time to time. So you have accelerators, you have reduplications, you name it. So all these tools and techniques actually have been very helpful to improve the computing performance. The problem is that if not all of them, most of these optimizations have created some sort of security vulnerabilities. And some of them we are going to see today. So, for instance, around the memories, around the caching, around out of order and speculative execution or branch prediction, they all seem very harmless and very, performance oriented optimizations, but they do leave some loopholes. So I'm just going to show you today some of these loopholes, and we are going to establish a case for how the security must be perceived from hardware perspective as well. So this is a very conventional look of Intel architecture. Basically, you have logical CPUs which are mapped on physical cores, and then you have some shared memory, and then you have some dedicated memory. So usually you have local level caches, L1 and L2, then you have third level or last level cache, and most of these memories are inclusive in nature, which is a property to maintain data coherency and consistency. Coherency inclusivity simply means that all the memory levels will have an updated copy of data that you're using. So I'm just showing you this because we are going to establish the future discussion around how a conventional architecture is basically organized. Now, moving on with this. Now, based on this understanding, I'm just going to highlight a few basic concepts which actually converted into vulnerabilities. So, for instance, we all know that memory is organized in a certain hierarchical fashion when it comes to computing. So, from the closest and the fastest level of registers to farthest and largest level of disk storage. So, you have caches in between, you have RAMs, you have disk storage, and you have a certain number of registers available to the CPU to do the computation. Now, the take home point here is basically that data can be present at any of these levels. And if it is inclusive, it would be present in most of these levels, right? So just keep that information in your mind when we come to next slides, that memory has a certain hierarchy to follow. Now, memory is also organized in order to favor locality, and locality in both ways, in temporal as well as spatial. So by definition, by temporal locality, we actually mean that the data being referenced are more likely to be referenced again very soon in a certain time window. And spatial locality is simply that if processor references a particular data item at a particular address, it is more likely to reference other data items in the same spatial locality. So memories, when we design them, we organize for locality. So we actually take care of both temporal as well as spatial locality. Then another property around memories is that memories are short. We have seen the evolution of memories. So it is never enough. So what we do is that we try to create techniques to reduce the memory footprint of your system or of your applications. So we apply different processes. We apply deduplication of information. We apply shared libraries so that multiple processes do not duplicate same instructions, or if it comes to data as well. So we have many optimization techniques that allow us to reduce the memory footprint of your program because of the limitation on memory size. Again, memory is organized in a certain fashion. So I'm not assuming that all of you know about this, but still, this is just a representation, a very high level representation of how your memory is actually being accessed. So if you have cache memories, you have a particular address being generated by your CPU. It has certain fields to actually identify from where to load the data. So data is loaded into specific sets depending on the address, and cache line is loaded into specific ways. So this is simply to illustrate that the memory is organized in a certain way. And when you generate a particular address to access data, it has certain fields which correspond to that organization. Now, with this four elements, let's have a look at why it is a problem, why we call them as vulnerabilities or potential vulnerabilities. So I actually like this statement from 2018. Um, Patterson and Hennessy, these are the two authors of the most utilized, reference book on computer architecture. So they, in a conference, stated that the state of computer security is embarrassing for all of us in the computing field. And why they had to say that? Because now let's get back to what we just discussed. We have memories which we have a shared memory architecture in order to offer smaller memory footprint. So we do optimizations so that multiple programs can share the same memory space, and they do not increase your memory footprint. So shared libraries or deduplication of data leads to planned or forced cache eviction. Why? Because when you share a particular location, let's say two programs intend to use a particular instruction, and that instruction is deduplicated on your memory. So it has a direct access on one single location. So it actually allows one process to access the same address as the other one is accessing. So this is kind of an opportunity to reveal the organization or the location of certain instruction or data in your memories. Similarly, we just discussed that memory is organized. So memory organization is done in order to offer better addressing modes so that you can immediately figure out where to find the information. Just like we do in a library setting, we know that the sections are dedicated and you just go to that section and find out the information there. Similarly, memory also is organized in a certain fashion to offer better accessing modes or addressing modes. But that organization actually exposes the structure of address space. So if you know in a certain way a memory is organized, you can actually attack that structure itself and figure out how you store information. Similarly, we just talked about the inclusivity, which means that data is present at multiple levels in the same way. So it actually offers data coherency to maintain logical correctness. But in order to do so, you also introduce certain instructions which perform certain operations to maintain that coherency. For example, in Intel case, you have an instruction called CL flush, which actually allows a process to access cache line with a full privilege. So if that is possible in a shared context, if one process is allowed to remove the instruction or data of another process, we have a problem there. Again, cache memories, it's a type of memory being introduced in computing architecture for better performance. It offers better access time, but it also allows distinction between access times. And we are going to see this thing in the new slide, next coming slides also, that how this information can be actually uh, uh, harmful. So I'm just going to move a little faster now because I see that I'm running a little out of time. So side channel information is actually always been there, but the real question is anything wrong with measuring the memory access latency or profiling cache utilization when it comes to analyzing performance? No, absolutely not. But if you're doing the same thing for different alternative purposes, for example, if you're using memory access latency measurements to infer keystroke timings, or using the information on cache utilization to observe cryptographic keys, yes, definitely that is wrong. So in principle, there is nothing wrong with having side channel information, but obtaining metadata and deriving secrets from that is wrong. So based on this understanding, I'm just going to quickly show you some side channel attacks. Um, uh, if you have any questions, maybe you can even ask during. Okay, so let me just see. Okay, so this is just the same illustration showing you that cache-based side channel attacks have been uh, trying to extract information across all levels actually. So it is not limited to memories. We have attacks which target main memory. We have attacks which target the caches. Then we have attacks also which target the computational part of it. So attacks are targeting both computational as well as storage part. So here is some perspective that, for instance, if you take caches, well, caches are organized in a certain way. So that organization, if you have a look at, for example, two-way set associative cache, you can have multiple processes mapped to the same set, and one process out of the mapped processes might be an attacker and the other one might be a victim which you're trying. But because of the same mapping, it gives an opportunity to exploit this information. So there are attacks like prime and probe, flush plus reload, flush plus flush, others which actually exploit this kind of information. Similarly, you have computational attacks, which actually exploit the way computational optimizations work. So for instance, if we talk about out of order and speculative execution, the principle is to actually fetch instructions in order, compute them or execute them out of order, and commit them in order. So this information is also being exploited by some of the attacks out there. Uh, this is a very dense slide, but I hope it will give you some information about where to look for. So it actually shows what are the attacks, how are the defenses working, what are the memory levels these attacks target, how is the performance degradation around. So I hope you're having the recorded slides afterwards, so you can use that information. So it's not that there are no defenses out there, but uh, today the defenses against hardware security are mostly lagging behind. So there is no one particular way of looking at this and targeting. So mostly you have vulnerabilities exploited, and then you have mitigation or countermeasures being patching them up, and then there is new vulnerabilities being exposed. So I'm just going to show you a couple of cache-based attacks first, and then we are going to move on computational attacks to actually make sense of what we just talked about. So a few slides, if you do not know caches, well, 101 on caches is basically that you have a RAM from where you want to access certain information for computation. So you need to perform computation at cores, and you need to have access to information. So when you access information, let's say we are trying to access A1, if you access it from the main memory, well, it would take longer time. Obviously, the RAMs are farther than the caches. But in the process, while doing so, you will keep a copy in the cache. You will first access the information from the main memory, put a copy in the cache, and from there you will provide it to registers for computation. The next time when you access it again, it would be faster because now you will have a cache hit and the information is available, and it would take shorter. Now already, uh, well, alternatively, this is just again the same illustration showing that the first time you access the variable I, it would request to the cache, it would have a cache miss and request all the way from RAM, and it would respond and it will be provided. But the next time when you access, it is in the cache and you have a cache hit. So the information that is important here is that if your malicious program knows this, and which is very obvious information, so it would know that first time when it accessed the variable I, it took longer, and that means that the information was coming from the main memory, and which means that the information was not available in the cache. And the second time when it takes lesser time, it implies that the information is right now available in the caches, which means that somebody other than this process might also be using this information. So distinctively, you can actually generate a very clear pattern of what information is present in the cache and what information is not present in the cache. And in between, you can actually put a threshold explicitly, distinguishing between the information available in the cache and information not available in the cache. And this is, one of the measurements that you can do in your own, settings. Also, if you know about the caches, there is a certain organization, memory, due to being, programs being large, most of the data or instructions are mapped to the same set. So when you need to reuse particular variable which are mapped on the same set, it would create a cache eviction. So for instance, if you had the set one being being filled with variables from A to D, and you needed to place variable E, and it was mapped to the same set, well, you have to replace any of the ways, and you can have different policies to do that. So this is another feature which is interesting and can be exploited by a malicious program. So based on this, let's have a look at some of these attacks. So cache-based attacks can be categorized into physically shared and unshared memories, and some of them are listed there, but this is not an exhaustive list. You can have more, and recently there have been many actually. So let's have a look. This we have talked about, so I'm just going to jump right next or the next slide where attack is being demonstrated. So this is a typical attack cycle where you have an initiation, a wait state, and then an observation. So an attacker would initiate a certain state of your memory, wait for your victim process to execute, and observe what happened, what the program actually did. So even the stealthier attacks leave behind certain footprint, but we are going to see that in a while after looking at the attacks, that how that information could be used to detect these attacks. So let's have an illustration where you have a victim process, let's say your cryptographic operation, and you have an attacker process or a spy process, which actually tries to see what is being accessed by your victim process. So what happens is that we are taking the assumption that attacker and the victim have a shared library to access. So which means that an attacker has its instruction mapped to the same location as the spy. And this sharing would allow one process to look into the address space of the other process. So there are a couple of attacks which exploit this information. So there are, we are going to see three of them: flush plus reload, flush plus flush, and prime plus probe. Let me show you how they work. So flush plus reload is one of the early attacks which exploited this kind of feature, where you have a shared library being accessed by two anonymous processes. And we assume that one of them is a normal process doing some operations, and the other one is actually a spy process trying to exploit the information being processed by the victim. So let's say a spy maps itself to the shared library, and as a first process, using certain privilege instructions, the spy process actually flushes this particular location deliberately. Now, since the spy process has deliberately flushed this particular location, it lets, so this is the initiation phase, if you see. So the spy has done its initiation of attack, and then it lets the victim process execute, which is a wait state for the spy process. So it let the victim access. Now, remember the information that we just discussed, that if the victim is going to access this data item, it is going to either have a fast access or a slow access, depending on the fact that whether the data was present in the cache or not. So it lets the victim execute, and then it probes that information again, the spy process. It reloads that same location again. Now, there are only two possibilities now for this spy process. Either the reload would take less time, or the reload would take more time. And you already have understood what information it would reveal. If the information is being extracted out of the same location in a lesser amount of time, it actually reflects that there is a cache hit, which means that the data was being there, which means that the spy had actually flushed this location deliberately, and now the data is present again in that location. It only implies one thing, that the victim process is actually using this information, because while the spy process was waiting, the victim process actually loaded this information in the shared location. So the spy would know that from this location, the victim process is actually using this information right now. Otherwise, why would have it loaded the information? So this is already a revealing of information. So all those locations where you have sharing, and the address space is mapped, the spy process can actually extract all the access pattern of your victim using this method. So this is a measurement that we did in our own lab, and it shows that it is distinctively possible to figure out what is being measured by the or computed by the victim. Similarly, flush plus flush attack is very similar to the same approach. It actually flushes as a first step to initiate the attack. It waits for the victim to load the data, and then it flushes again. And this time, it only measures the same timing by looking at how much time the flushing took. So if the data was present or absent, it would have a very different signature on the timing. Similarly, you have prime plus probe attack, which is slightly different from the last two. In this attack, the attacker actually fills in the entire cache space or a certain calculated amount of space, and then it let the victim execute. So victim would actually load its own data, which means that whatever spy had loaded, it would use the eviction property and replace that data onto those locations. So for example, these two locations were being accessed by victim, and now the spy actually accesses its own filled in information and sees that if the access is slow, it means that the information loaded by the spy is not there. But if the access is fast, it means that whatever the spy process has put in the cache, it is still there, which means that it was not, the location is not of interest by your victim. So, these kind of attacks actually reveal a lot of information. And there are plenty which use the same principle, but it's not the end of it, because there are solutions to redesign cache so that such information is not being leaked so easily. So in literature you will find a few solutions which are there: scatter cache, scissor cache, indirect eviction cache, mirage, and so on. I've just listed a few to give you an idea if you are working in this area or you intend to work in this area. So you can dig the papers and read them and see what is there for you. So I'm just quickly going to show you one of them, which is indirect eviction cache. Basically the idea is that if your attacker knows that you're going to, for instance, in a prime plus probe case, where the attacker actually fills locations of its interest and let the victim execute to figure out which locations are being touched upon by the victim. You can actually camouflage that information, because it is based on the fact that there is a direct relationship between the incoming victim address and the already primed addresses by your attacker. So if you can break this direct relation, you can actually make it difficult for the attacker to extract the eviction set. For instance, hypothesis here is that if you can use indirect eviction of cache lines, it will make the prime plus probe type of attacks impractical, because they are based on the direct relationship between incoming address and outgoing evicted candidate. So in this work, this was done by one of my PhD students. So actually what he proposed is that simply you make the eviction set larger, and that would basically make it, on one hand it would make it difficult for the incoming for the attacker to create a relationship, a direct relationship with incoming victim address, and it would also make it irrelevant for the attacks which are based on the philosophy of priming and probing later on. So I'm just going to be very quick on this. I think I've already consumed my time, but no eviction cache lines are impractical. Non-eviction cache lines are impractical to find such kind of attacks in this case. So this work was given Best Paper Award in 2020 by a very good conference. Um, I can I take a few more minutes, Nazars, please?
Yeah, sure, Dr. Huram, because we do have a 15 minutes break after this session and we can consume some of that.
Okay, so I'll just take some more minutes, because sorry for that, because I planned my slides and I took a little more time. So I'm just going to quickly show you some computational attacks as well, because they are very interesting. They were actually reported in the mainstream media as well, so they are of interest for your listeners, because they exploit the way we actually use the computational optimization. So there are two very famous attacks, Meltdown and Spect. They were reported in 2018, and there were variants of these attacks later on. And basically, they exploit out of order execution and speculative execution. So we are going to just see quickly their working principle. So what they do basically is they remove isolation between your kernel space and your user space, and they have the capability to read your entire RAM. So, if you look at the meltdown attack, basically the vulnerability that the meltdown attack exploits is the permission check for address, which is done in parallel to the out of order execution. So, what happens is basically whenever you have a permission check to access certain location in the memory, the kernel memory, for instance, if being requested for access, the program, your operating system would allow the out of order execution on the projected path of execution and perform the access checks in parallel. Now, it takes certain time, and if the permission check is failed, it would simply interrupt the execution which was being done and discard the results. Now, it is it looks fine that you just tried to improve performance by computing in anticipation, and when the check was not allowed, you actually you know simply discarded the results. But the hardware keeps a footprint. Basically, that information is already being fetched to your memories, your cache memories, and the cache updation mechanisms are based on when you need to replace a particular data. So the data that you brought in would reside in your caches and will only be removed when needed. So even if you do not allow a particular program the access permissions, your hardware has already done half of the job. It has already accessed your data and put in the caches. So for example, this is some of the results that we generated here in the lab. It actually shows that, for example, it shows that total number of instructions of a process being running and the number of page faults that it generates. So if you look at the blue one, it shows that there is a process which is running the meltdown attack. Actually, it has not many instructions. It is actually one of very low on the number of instructions. However, the number of page faults it is generating compared to others is relatively outlier. So it only reflects that something is wrong with this process, because it is actually not a big process. It is actually a very small piece of code running, but it is excessively generating page faults. And page faults are generated when you don't have particular access permission. It actually revealed that the process was trying to apply a meltdown attack on your kernel. So well, again, you can see the same pattern in different measurements, but I'm going to skip this one to show you the other one. We did apply some machine learning algorithms to actually extract the the running attacks. You will have the slides so you can see if you're interested. There are papers out there with our names, so you can find them. Spect attack, on the other hand, is actually exploiting your conditional code. So speculative execution of branches is being exploited by a Spect attack. And what it does, it basically mistrains the branch predictor to convince the CPU to speculatively execute the code which should not be executed. So, I mean, if you know how branch predictors work, whenever there is a conditional code, you anticipate that it is going to take uh, either path. So, if you take an assumption, for example, that whenever there is a conditional code around a bound, the bound is going to be true, so it will take one particular path. So rather than waiting for the condition to be resolved, you start executing your code on that path. And if it is true, if whatever you predicted was actually right, you get a speed up. If no, you get a slowdown. Similarly, if either you can predict the condition to be true or false, either way, if your prediction is correct, you get a speed up. If your prediction is false, you might get a slowdown. Well, you definitely get a slowdown, but in addition to that, you might risk certain information leakage because of the same reason, because you went on a particular path to execution which was actually not recommended by the conditional bound. So we did the same exercise with these attacks, and we figured out that again, a Spect attack, which is the blue line here, is very small in terms of footprint, but it generates a lot of branch mispredictions. Why? Because it is a process deliberately trying to push your predictor in the wrong direction. So, and then you can have more results on the cache access and cache patterns. I'm going to skip this one. So, conclusive slide. Basically, attack surface, which is basically the fact that attacks are being all over your hardware, it is expanding continuously. So you can have information retrieval attacks that are software in nature and trying to extract information from hardware. There are attacks which are software in nature and trying to extract information from software, and similarly hardware on hardware and hardware on software. So the attack surface has all these combinations of attacks which are out there. And what they try to do is they try to either attack the protected software or the environment that protects that software. So in the follow-up around 1:30, I think you have a demo from the team, which would actually show you the Intel SGX protected environment execution of some blockchain code. And there you can see also that how these attacks can actually, you know, exploit this information. So for those of you who want to pursue some research work in this direction, there are some open research questions, and I will close with this, that security challenges are emerging from the way we compute today. So there was nothing wrong because it was done for the purpose of performance optimization. But today it is not the right way of computation. So what radical changes are required both at hardware and software level? So this is one of the major research challenges. Computing platforms are not secure today and attack surface will expand further. So what tools and techniques are required to contain existing vulnerabilities first? Okay, architecture redesign would take, a lot of effort and time. So what can we do today to actually contain these vulnerabilities? And how to ensure future systems are secure by design? So this is a possible roadmap that most of the research community is convinced to do. So at first you need attack surface assessment, which is in order to establish that how vulnerable we are today. Then there are two parts to work on: operating system and hypervisor, to actually contain, permission check issues, and provide isolation wherever it is possible without compromising on the performance, and obviously to redesign the architecture in the long run to provide that fundamental security by design. So with this, thank you very much for giving me extra time as well. This is the demonstration that you will see around 1:15 today. Thank you very much. You have my email address. If you have any questions later on or now, please go ahead.
Thank you very much, Dr. Kuram Bhatti, for the wonderful session. And I really hope that our participants not only enjoyed it, but also learned a lot. So there is a question, Dr. Kuram, if you would like to answer it, participant is asking about, sir, there are various antiviruses that are being updated every day. Are they playing any role in this challenge?
Yes, of course. Antiviruses, again, as I started my presentation, the general perception at large about the security revolves around the software security. So antiviruses primarily look into the software vulnerabilities. We do have a couple of slides which actually can show you the regularly reported, new vulnerabilities every day in the software, but they hardly play any role when it comes to hardware vulnerabilities. Hardware vulnerabilities require a particular, setup to detect at first, and then you also need to patch them up with, there are detection solutions readily available. Yes, you can actually use those detection modules to at least establish that there is something wrong with your hardware. But solutions are actually more than that, because if you need to patch a hardware vulnerability, and if it is generating, for example, from the way your memory address space is being exploited, I really doubt that any software antivirus, which you call, can actually save you from that. So you need to actually patch it at the hardware level, from where the vulnerability is being actually originating. So yes, detection can be done using such software packages. Mitigation, it's hard to say.
Thank you, Dr. Kuram. We do have
Yeah, there
another
is another
question.
question about SPECT. Yes, the answer is yes. We have a paper on SPECT detection. If you are interested, please drop me an email. I'll send you. Hafizur Rahman, I think, asked a question about this. So we have worked on both SPECT and meltdown detection and mitigation both. I can share with you some information, and you can see that.
Sure. Thank you very much, Dr. Kuram, for the amazing session you have just delivered. And after that, we will be having demonstrations, as Dr. Kuram just mentioned. So our next demo is at 11:45. Until then, I do have few announcements to make. First of them is many participants are asking about recording and certificates. So yes, both of these things will be available after the conclusion of this 3-day workshop. Blockchain Security Lab here at ITU will be delivering those certificates, and recording will also be shared with you guys. So on this note, I would like to thank Dr. Kuram again for his precious time.
Thank you
Thank
very
you,
much.
Dr. Thank you. So our next session is going to start at 11:45, and we do have these 4 minutes to take a little break. So I would request you all not to leave the session and just mute your mics and turn off your cameras and be back at 11:45 sharp, so we can start with the demo. And demo will be delivered by our researchers here at ITU Blockchain Security Lab, Mr. Zubair and Mr. Talha. It will be a half-an-hour demo, and I really hope that this will be very fruitful and very good learning opportunity for all of you. So see you all at 11:45 sharp. Thank you. So welcome back, participants. We are back in our regular sessions. So now we are going to have a very amazing session by our fellow researchers, Mr. Zubair and Mr. Talha. Mr. Zubair have delivered a session last day, and this is a follow-up session of that. So I guess Zubair is ready to present. Over to you, Zubair.
Okay, thank you, Hamid. Okay, guys, welcome back to the day 2. We left at the transaction. We will looking what a transaction looks like and what is the impact of transaction in the blockchain system. I will walk you through the remaining stuff we left today, yesterday, and after that, Mr. Talha will go you and walk you through the code and Solidity programming after this session. So, what a transaction? We see if you may want to make any change to the blockchain network, you want to update the state of a blockchain network, you have to establish a transaction. So a transaction is nothing more like a bunch of instructions. If I want to execute a code on the smart contract, otherwise I want to transfer some ether to other account. I just have to establish something like I have to provide a receipt address in which I want to say who will receive ether or which smart contract I want to call. After that, I provide sender address. What a sender address looks like. Sender address says who is originating a transaction. A transaction is always originated by an externally owned accounts. A contract cannot originate a transaction on its own. Here, a contract can actually originate a transaction, but on the behalf of an EOA transaction. So let's say I send a transaction to a contract and I say, okay, call another contract and update its state. In that way, a contract can originate another transaction. But those transactions are called internal transactions, and they are not, they are not stored or there's no record of those transactions on the blockchain actually. All the transactions you see on the blockchain are actual transactions originated by EOA accounts. So, and we will see how miners execute those transactions sooner. So every transaction has a fees. We can see that a signature transaction structure actually include a signature. What is signature? Basically, whoever is originating an transaction. Let's say I have an account. I have an Ethereum account, and I have a public address. I have a private key. If I want to originate a transaction, I have to actually sign it so that I don't say in future that I didn't originate that transaction. So to maintain non-repudiation, we actually have to sign the transaction, and we cannot post it without signing. And other fields, transaction includes value, the amount of ethers we want to send, the data actually in bytecodes. It's not like in high-level language or Solidity. It's a bytecode. We'll see what it looks like. Gas limit. Yesterday I mentioned what is gas limit. If we specify a gas lower than the gas limit, and the function or our smart contract or our transaction needs more than that, then our whole gas will be consumed and our transaction will fail. So we have to specify an satisfactory level of gas limit, because if the gas is more than we specify, let's say I have to specify 5,000 gas and my function only need 2,000 gas, so remaining gas 3,000 gas will be returned back. So there is no worry about that. So after that we have nonce. Nonce represent how many transactions are already made by a particular account. So let's say I have an account XYZ, and nonce represent my number of transactions. Maybe I made 5 transactions, 6 transactions, and we saw that a minimum transaction gas cost on the Ethereum network is 21,000. There's no operation lower than that. So this is a simple transaction. You want to send any ether from one account to another account, you have to specify 21,000 gas. All other for smart contracts, all other things require more than that. So this is basically a transaction object looks like in any language, let's say JavaScript. So we can see known, gas price, gas limit, all the stuff specified here, to address. And if we can see VRF, this is basically signature parameters, and data actually is very short here. Maybe it's just like calling a function without any argument. It's maybe a getter function, something sort of stuff. So we are moving on to the next thing, that is block. What a block is, we previously saw that a block is actually a group of transactions, and that's true. Block is nothing more than that. Actually, block contains some other stuff too that is very local to the block, but the whole purpose of a block is to contain the transactions in a single place, let's say. So we can say here a block structure contains a timestamp, when the block was mined or created, block number, actually what is the number of the block until the starting of the blocks. Difficulty. Now this thing I will discuss in mining, which is just after this slide, I think. So difficulty represents how much difficult is it for the miners or the nodes to solve that puzzle we were talking about yesterday. So difficulty represents that thing. Parent hash, what is the hash of the previous block? So this is the parent. We say parent because it was before that block, and that block helps generate current block. That's why we call it parent. So this parent hash represents the block hash of previous block transactions. This contains all the transactions, not complete transaction. We saw transaction looks like this. No, not this whole stuff. No, just the hashes of transactions are actually appended in the block. Okay, and all the hashes in the block in an array format. And then we have state root. Okay, so there's something interesting. What is actually state? We saw the state actually represent the storage in EVM where all the your local variables of the what we say smart contracts or any balances or anything is stored on the blockchain. The storage area basically. So the storage area and the local variables are smart contracts, all hashes. On the Ethereum network in general or on the blockchain in general, we have hashes to identify everything stored, or we have hashes for the transactions, for the blocks, for the storage, it is anything. A state is something more technical. If state root is technical term, I will not go into that. Just if you want to look it what into it, you can always search for the Merkle trees. It's a basic concept in which we maybe combine different hashes to produce a single hash, and we always can traverse back to the exact root, exact point of storage to retrieve the actual data. So a block actually contains a single hash of all the states stored on the EVM. So a mixed hash is a unique identifier of the block. It's the hash of the block. Nodes represent another interesting thing. I will skip for the moment and we'll see in the mining section. Miner is the person who actually created or mined the block. Gas limit the same, just like we specify in the transaction. But here it is not about the block. It is about all the sum of the transaction. Let's say a block contains 10 transactions. So each transaction has a gas limit. What we will do, we will sum up all the transaction of all the we will sum up gas limit of all the transactions, and it will be the gas limit of this block. Gas used represent how much gas was actually utilized while executing all the transactions. So a typical block has an up to maximum of 50 million gas units, which means if you sum up all the transaction gas limit of all the transaction and it is exceeding 50 million gas units, we cannot add those transactions in one block. We have to divide it into several blocks. It can vary. It can go up to 30 million. If we want to change, we can actually change it in the Ethereum network, but it cannot be more than 30 million gas units for one block. So this is some sort of structure looks like a block. We can see there's a difficulty, extra data, just ignore some stuff here. There's more technical terms. If we want to go depth, you can always email me and we can discuss what it looks like. Because for the beginners, for the getting started, these things we can ignore for the moment. So there's a hash, mixed hash, all sort of stuff written down here. This is an actual block looks like. If we print it in our language, get it from the blockchain and put it in a simple language like JavaScript or something like that. So the first ever block created in the blockchain is called Genesis block, and it has no parent hash because it is the first ever block. There is no parent. So it is the parent of every other block in the chain. So Genesis is where we don't actually specify any code or something like this. It is just the first block in the chain to get it started. Now the interesting part is here. What is mining? Many people actually think about that the mining is a very, very technical or very, very difficult stuff to consider. And वो सोचते हैं पता नहीं को बला चीज है यहाँ पर mining. जब भी बात होती है Bitcoin mining की पता नहीं क्या करना होगा. Actually the stuff is very simple. Stuff is actually very simple. The miners are not doing something innovation, are not solving some magical stuff. They are doing one simple stuff. We will see what are they actually doing. So the actual process mining referred to is in proof of work accordance is creating a block and adding it to the blockchain. Okay. So how it begins, how it starts, how miners actually start their work. So first of all, let's say I want to transfer 1 Ether to my friend. And what I do, I create a transaction, I sign it, I post it onto the blockchain. Now it is pending into the pool. There are a bunch of other transactions are there. So a miner will do, what a miner will do, it will pick a transaction from the pool. Maybe it's mine, maybe others. Let's say there are a bunch of transactions and they include mine transaction as well. So he will create a potential block. He will form a block structure, include everything there. He will execute my transaction. He will validate my transaction that actually my transaction is valid. I am sending one ether. Do I have one ether in my account as well? So all that sort of stuff, all that sanity checks he have to perform before actually making it to the block. And after that, interesting thing comes in. He has to guess a puzzle. We were talking about puzzle yesterday, that he has to guess a number after million of tries. He will figure out that number and he will compare it to the condition. If condition matches, he actually guess the solution and he will post the solution to the whole network to verify it. So this is where proof of work generation comes in. So if we see what actually solution is, what actually he has to do is, what he has to do is he creates a block header. Block header contains all the information we just previously seen: timestamp, knowns, that stuff, those stuff, all that thing, transaction, IDC, सब कुछ block के header में पड़ा होता है. So क्या करता है एक माइनर हमारे पास यहाँ पे, वो करता है कि previous जो block होती है उसका hash लेता है, one part. The second part is he has to maintain, he has to change every time a knowns, a number. He has to guess that number. That's it all. That's the whole purpose of the mining, or the miners, or the GPUs, or the whole electricity power in proof of work is just guessing that number. So I am repeating again. He takes the hash of the previous block, he guesses a number, he hashes that number, he mixes two hashes and then compare it to the target hash. Let's say a target hash, compared to the target hash. And if his hash is less than or equal to the target hash, which means he has found the solution. And if this is not the case, he has to repeat the whole process again. You see, अब हमें तो लगता है कि यार ये guess number करना तो that's very easy. You can spin up a node and you can say, okay, do guessing your number. You are a machine. You can do trillions of guessing in a second. Go ahead. But that's not the case. It is ये कोई ऐसा सीन नहीं है कि उसने 1 से लेकर 10 तक नंबर नहीं गेस करने, उसने ट्रिलियंस में, क्वाड्रिलियंस में नंबर गेस करने हैं. उनके कॉम्बिनेशंस इतने ज्यादा हैं. सो देयर अब टारगेट डिफिकल्टी होती है, वो कौन सेट करता है? ये प्रोटोकॉल जो थीरम का वो सेट करता है, ईवीएम सेट करती है, थीरम का प्रोटोकॉल सेट करता है टारगेट डिफिकल्टी. और जैसे ही जैसे नोड्स बढ़ते जाएंगे नेटवर्क के अंदर, डिफिकल्टी हैज टू बी इंक्रीज्ड. व्हाई? टू मेंटेन अ कंसिस्टेंट ब्लॉक टाइम. Maybe I forgot to mention, in Ethereum we have 15 seconds block time. So he has to maintain that block time on the Ethereum network. So जो होता है हमारे पास नेटवर्क, वो ऐसी डिफिकल्टी क्रिएट करता है कि जब भी कोई सोल्यूशन बिल्ड करना शुरू करे तो ऐसा नहीं है कि उसे 1 सेकंड में सोल्यूशन बिल्ड हो जाए, और ऐसा नहीं है कि हमेशा 15 सेकंड ही लगेंगे. एवरेज 50 सेकंड, इट कैन बी 10 सेकंड, इट कैन बी 20 सेकंड्स एज वेल. तो जो एवरेज होती है वो 15 सेकंड की रखनी होती है. एथीरियम के ऊपर, बिटकॉइन के ऊपर 10 मिनट्स की होती है. और इसके साथ साथ का और पर्पस भी होता है डिफिकल्टी का कि लेट्स से अगर मैं मैलिशियस बंदा हूं और मैंने बहुत ज्यादा नोड्स इंट्रोड्यूस करवा दिए, और अगर डिफिकल्टी कांस्टेंट है और मे बी मेरे पास पहले 50 नोड्स थे ब्लॉकचेन में और मैंने इंट्रोड्यूस करवा दिए 1000 नोड्स, मैं आई एम अ मैलिशियस पर्सन एज वेल. सो मैं क्या करूंगा, अगर मेरी डिफिकल्टी कांस्टेंट है तो मेरे हायर चांस हो जाएंगे सोल्यूशन को जल्दी गैस करने में. तो मैं क्या कर सकता हूं, मैं ब्लॉकचेन को कंप्रोमाइज कर सकता हूं. अब यहीं पर हम कहते हैं कि ब्लॉकचेन इम्यूटेबल है. इम्यूटेबल क्यों है? जब आप एक ब्लॉक का सॉल्यूशन गेस करने में इतनी देर लगा रहे हैं और आप कंपीट कर रहे हैं होल नेटवर्क के साथ, उतनी देर में बाकी नोड्स नेटवर्क भी सॉल्यूशन बिल्ड कर रहे हैं. तो अगर आप एक ब्लॉक को कंप्रोमाइज करते हो तो आप जब उतनी देर में आप उस ब्लॉक को पोस्ट करोगे नेटवर्क के ऊपर, उतनी देर में और ब्लॉक में जुड़ चुके होंगे. सो यू हैव टू चेंज ऑल अदर ब्लॉक्स टू. और अगर ये इंस्टेंटेनियस हो, लेट्स से 1 सेकंड में सॉल्यूशन फिगर आउट हो रहा, तो यू कैन इजीली चेंज ऑल दोस ब्लॉक्स. इवन तो ये थोड़ा डिबेटेबल है कि इसमें एक्चुअली कैसे होगा स्टफ, क्योंकि प्रूफ ऑफ स्टेक में आप कहेंगे कि वहां पर तो कंपटीशन नहीं होता, तो वहां पर आपकी बात गलत हो जाएगी. वी कैन डिस्कस इट इन मोर डिटेल, बट फॉर द मोमेंट वी आर आल्सो रनिंग ऑफ शॉर्ट ऑफ टाइम बिकॉज़ वी हैव टू डिलीवर अनदर solidity programming session. So I will just conclude it after this slide. So माइनिंग में उन्होंने माइन कर दिया, ब्लॉक बना दिया, सॉल्यूशन गेस कर दिया, पोस्ट कर दिया. बाकी सारे नोड क्या करेंगे, उस सॉल्यूशन को लेंगे और फिगर आउट करेंगे कि करेक्ट है कि नहीं है. हैशिंग की सबसे प्यारी बात ये होती है कि उसको बनाना शायद मुश्किल हो, लेकिन उसको वेरीफाई करना इज जस्ट इंस्टेंटेनियस. सो बाकी सारे नोड्स को क्या करते हैं, वेरीफाई करते हैं कि एक्चुअली इसने जो सोल्यूशन बिल्ड किया है दैट्स करेक्ट, और आफ्टर दैट वो अपनी लोकल नोड्स की कॉपी को भी अपडेट कर देते हैं न्यू स्टेट के साथ, और ट्रांजैक्शन जो है वो कंफर्म हो जाती है। और करंट जो माइनिंग रिवार्ड है थीरियम के ऊपर अभी 2 ईथर्स है, ये रिड्यूस होता रहता है टू अवॉइड इन्फ्लेशन ऑन द ब्लॉकचेन। So transaction life cycle I just explained in the mining. रॉ ट्रांजेक्शन आई, पोस्ट हुई, साइन हो गई, उसके बाद पूल में चलेगी, माइनर ने उठाया, एग्जीक्यूट किया, स्टेट्स अपडेट हुई, ट्रांजेक्शन कंफर्म। दैट्स ऑल, दैट्स द होल पर्पस ऑफ अ ट्रांजेक्शन एंड माइनिंग स्टफ। You can also see it in this slide as well. A user, उसका इथेरियम का क्लाइंट है, उसका कुछ एड्रेस है, वो अपनी ट्रांजेक्शन बना के साइन करके पोस्ट कर रहा है, माइनस बैठे हुए हैं, कोई ना कोई माइनस उठाएगा, उसको एग्जीक्यूट करके सोल्यूशन बिल्ड करेगा, ब्लॉकचेन पे पोस्ट करेगा, एंड बाकी सारे माइनर्स बाकी सारे नोड्स को वेरीफाई करेंगे और वो ब्लॉकचेन का पार्ट बन जाएगा और सबकी स्टेट भी अपडेट हो जाएगी। अब यहाँ पर कुछ अंकल्स का कंसेप्ट भी आता है, लेकिन फॉर द मोमेंट लेफ्ट इट कि अंकल्स क्या होते हैं। जस्ट क्योंकि मैं आपको एक हिंट दे देता हूं कि ब्लॉक सिर्फ एक बंदा ही नहीं बना सकता, सारे बना रहे होते हैं, तो ऐसी सिचुएशन भी हो जाती है कि मल्टीपल नोड सॉल्यूशन पोस्ट कर देते हैं, तो फिर उनमें से किसको मेन आपने माइनर अज्यूम करना है वो मेन माइनर बन जाता है, और किनको आपने रखना है बाकी, जिन्होंने बाकी भी सोल्यूशन तो बिल्ड किया, आपने इलेक्ट्रिसिटी पावर तो लगाई है, उनको भी कुछ ना कुछ रिवार्ड देना होता है। वी कॉल देम अंकल्स। सो डेवलपमेंट टूल्स हमारे पास जो है वो ट्रफल है। TOEFL is a very pretty good tool. Actually, you should always use it if you are getting started. फर्दर आप जाके TOEFL के बगैर भी सारा कुछ डेवलप कर सकते हैं, लेकिन TOEFL आप गेटिंग स्टार्ट के लिए बहुत अच्छी टूल है। किनाश सिमुलेटेड ब्लॉकचेन है। Web3.js एक्चुअली में जावास्क्रिप्ट की लाइब्रेरी है जो हम इथेरियम के साथ इंटरेक्ट करने के लिए यूटिलाइज करते हैं। Node.js इज अ जावास्क्रिप्ट रन टाइम एनवायरनमेंट। कुछ चीजें इनमें से आप लोगों ने देखी भी होंगी पहले। Express.js is a API framework, backend framework. MetaMask is a Ethereum wallet, browser-based Ethereum wallet, and VS Code is just integrated development environment. So I hope you guys enjoyed. अगर कुछ stuff रह भी गया हो तो you can always email me. We can discuss in detail. We can arrange other sessions as well. So I will. Okay, Talha, it's over to you. You can continue regarding the programming, Solidity program. Thank you.
Thank you, Zubair. Let me just share my screen quickly. Right. So, for the development of smart contracts or developing applications on blockchain, we use on Ethereum blockchain we use a language called Solidity. It's very familiar to JavaScript, as you can see. There's a contract which has a variable, and what it does, it stores a value and it returns a value. And this tool is called Remix. It's online IDE to compile, deploy, and test smart contracts. So I'll just quickly do this one. We have a contract here. Go to compile and we'll compile the contract. Some issues, I guess. Let me. Right. So the compiler has the contract has been compiled. We'll go to deploy and we'll deploy the contract. So the contract has been deployed. A transaction has been created. You can see the details. So the status is true. This is the transaction hash. This is the address from where the transaction was executed, and what was the payload of the transaction, how much gas it used, as Rubair described before. The details of the transaction all can be seen here. So quickly interact with this contract. So I'll just pass it a number. Let's say 10. So the number has been stored in the contract and a transaction has been created against it. So you can see here the function the dot store was called, and this is the encoded argument. So we pass the number 10, so encoded version of it. We can also retrieve the value. It will just show that the value is 10. Moving on, we have Truffle. Truffle is a smart contract development tool. It helps to compile, and deploy smart contracts. So we have an example here of full decentralized application. So this was just a contract. You can create multiple contracts and then you can attach front end to it to create a fully decentralized application. Moving on to the application, we'll first see the Ganache. So Ganache is a test network. So the smart contract cannot be changed once it's deployed on the Ethereum network. So you have to test the contract before deploying, and then you have to deploy it on the mainnet. So Ganache helps with that. It creates a simulating environment of a Ethereum network. You can deploy the contract on it, and you can interact with that contract. So without using the real Ethereum. And we have a MetaMask. MetaMask is an extension which handles your accounts. So right now it's to Ganache. I have a Ganache running here. So right now it's connected to Ganache and it's managing my addresses and its accounts. So we have a account 0DA9, starting with 0DA9. So here is that account. So I'll just quickly go to the this decentralized application. So this is the demo. We'll also show you how to build it, but in today's session we'll just go quickly over what it does. So this is a decentralized application for adopting pets. So you have different pets here, and you have a adopt button next to every pet. So if I click this adopt button, it will open the MetaMask, and it will say that do you want to make this transaction. So behind this adopt button, there's a smart contract is being called. So this is a smart contract transaction which is asking for my approval. So if I just confirm it, it shows success. Now these two have been adopted. I adopted this a little earlier. I just adopted this. So there's a smart contract. I'll just show you the code of it. So this is a smart contract. What it does is it gets a pet ID and it assigns a owner to it. So whoever calls the smart contract passes a pet ID, and the pet ID is allocated to that caller. So whoever calls the smart contract, he gets the pet. And function which just returns the values of this data sector. So this contract has been deployed, and this front end is interacting with that smart contract. I can also interact with the smart contract using Truffle console. I'll just run it. Truffle console, so you can run Truffle console, and it will open that console, and Let me paste it. Let me just type quickly. So I have access to the instance of the smart contract. I can call it function. If I call this, it will give me the list of the addresses who have adopted a pet. So this is my address, and this is the index of the dog. So 0th index and the 3rd index. So both of these dogs have been adopted by this address. I can also call this function directly from here, but it won't let me because account has not been coupled with this preferred console. So you need a theme address to make the transactions. But if you don't have that address, you cannot make the transaction. So if I call function, it probably won't let me execute it. Right. So okay. So I guess account was coupled with this preferred control earlier, so a transaction has been executed and just reflected. The log at the 2nd index will also be adopted. So whatever is being performed here can also be performed using a console, but we attach a front end to the smart contract so a user can use it. In the next section, next session we'll go over this tutorial one by one, and we'll show you how to build this application. So if you have any questions in a theme development, you can also mail me and I can answer your queries. So that's it.
Thank you very much, Talha, for the wonderful session, and also Zubair. So participant, do you guys have any questions? It's time to ask them. You can ask, and I guess Talha and Zubair would love to answer them. And if you don't, still let us know so we can move towards our next session. Okay, so Talha, we do have a question. A participant is asking, when we use Web3.js, is it query to MetaMask?
Where do you want to?
Okay. So Web3.js is not necessary to query MetaMask. MetaMask is a different thing, and Web3.js is a different thing. Mainly, we use Web3.js to communicate with the blockchain. We can actually create wallet, every stuff with Web3.js. MetaMask is an additional stuff to maintain an Ethereum wallet only. So Web3.js is a complete set of tools, libraries to communicate with the blockchain, post transactions, get transactions, execute functions, and that sort of stuff. MetaMask is just used to sign transactions and post those transactions. I hope it clears the issue. How the data storage is handled in dApps. So basically, in dApps, in smart contracts, we have local variables. जैसे आप जावा में अगर कोड लिखे हैं तो क्लासेस का कंसेप्ट आपने देखा होगा जावा के अंदर, तो जावा में आप टॉप लेवल पे वेरिएबल्स डिफाइन कर सकते हैं, ठीक है, वो आपके स्टोरेज होते हैं लोकल टू दैट क्लास. सो जस्ट लाइक दिस स्मार्ट कॉन्ट्रैक्ट के अंदर भी आप लोकल वेरिएबल्स डिक्लेयर कर सकते हैं, वो स्टेट लेवल वेरिएबल्स होते हैं, वो स्टोर करते हैं आपके सारे डाटा को. जैसे हमने अभी देखा था वो अडॉप्शन के कॉन्ट्रैक्ट के अंदर एड्रेसेस की एक एरे थी अडॉप्टर्स की, वो स्टोरेज एरे थी हमारे पास, वो स्टोर करती डाटा. हाँ मैं इन वन ट्रांजेक्शन एक्चुअली ट्रांजेक्शन इज अ सिंगल ट्रांजेक्शन, इसमें मल्टीपल ट्रांजेक्शन नहीं हो सकती, एक ट्रांजेक्शन में मल्टीपल नहीं हो सकती। आप एक ट्रांजेक्शन भेजते हो फिर आप दूसरी ट्रांजेक्शन भेज सकते हो। नदर पार्ट इज कि आप एक ट्रांजेक्शन में कितने फंक्शन कॉल कर सकते हो, दैट्स अनदर स्टफ के एक ही ट्रांजेक्शन में आप एक ही फंक्शन कॉल कर सकते हो एट अ टाइम।
सो डेटा स्टोरेज वाले क्वेश्चन में मैं एक चीज ऐड करना चाहूंगा। यूजली व्हाट हैपेंस इज दैट वी हैव front end, we have a back end, and we have a database. So in blockchain development, in Ethereum blockchain development, we don't have a database. All storage all the data is stored in a smart contract. So we can attach a database, but it's not a trivial task. So usually the data is stored, being stored in the smart contract variables. I hope that answers your question.
Awesome. Thank you, Talha, and thank you, Zubair, for answering these questions. And now it's time for our next session. So I would like to thank you guys again for the wonderful session. And now I would like to welcome our next speaker. She is Ms. Maha Ayub, and she will be talking about the demo of a spin-off of our research project named Transfer. So Maha will be presenting from the same machine I'm talking to you guys. So over to you, Maha. Thank you.
Assalamu alaikum. I am Maha Ayub, and here today I present the transfer, which is a storage state analyzer and extractor of Ethereum smart contracts. The agenda of today's presentation: first, we discuss about the background and the challenging factors and where the transfers lie, and then some experimental results we perform on transfer, and then the future works, and in the last, a small demo of the working of this transfer project. First, we discuss why we need a smart contract storage analyzer and extractor. As we know, blockchain technology is a tamper-proof. If some information become the part of the blockchain, it cannot be changed afterward. And Ethereum is a blockchain-based cryptocurrency, and smart contract is the main feature of Ethereum blockchain. So if a smart contract and their storage is deployed on Ethereum blockchain, then we cannot change afterward, or we cannot migrate into another platform or upgrade it. But due to some reasons, like performance issues, bug fixes, and security reasons, we need to update the smart contracts, their data or logic. But due to smart contract immutability nature, when we deployed the upgraded or logic of smart contract, it can get new space with new address assigned, and the old one remains back there. So what about our old contracts user data, and how we upgrade data into new smart contract or migrate the data into another platform? So here are some approaches that try to find the solutions to upgrade the smart contracts without upgrading their data, like data logic separation. In this approach, two smart contracts deploy on Ethereum blockchain. One smart contract represent and contains only the data structure of the smart contract, and the logics defines on the other one, and gets through the gets data or send data through external calls. So if some changes required in logic, it does not affect the storage contract. It's simply the new logical contracts still gets data from the old one with same calls. But if we change the data structure, then still we move on to the same problem on how to migrate the data. So in this logic, we can't change the data storage contracts if once deployed on the Ethereum blockchain. Our next approach is delegate based calls. It is same work as data logic separation, but the main difference is a new contract deployed called proxy contracts that works between the middleman, like between data and logic contracts. But for writing these contracts, the developers require the deep EVM knowledge and the further, which is difficult for the developers. And also these approaches, these two first approaches work only if we applied for the deployment of the smart contracts. But what about the contracts who's already deployed on Ethereum blockchain? How we extract their data or how we upgrade or migrate it? We have another approach, which is a replay transactions. And it again works only if a new contract are not change the data structure or logic. We can replay the old contract transactions and get the data state, but still if these transactions contain some information like runtime variables like blockchain timestamps and nonce value, something that we cannot replay it, then it affects the accuracy of replayed transactions, and we still face the problem of extracting the smart contract storage. So here's the transfer slice helps the users to extract, migrate, or upgrade their smart contracts with just few clicks without any concern of checking their same structure, logic, or any other limitations. So so transfer sense the need of automatic data extraction of smart contracts and provides the facility that helps users in analysis and extraction of storage state of smart contracts. So move on to the transfer technology. First, we get through the brief introduction of how this Ethereum smart contract storage lies and how it works. Smart contract state variables represent their state and get permanently stored on the storage tray and become the part of the Ethereum blockchains. And get permanently stored, which assigned to storage tray. Storage tray is an array of maximum size of 2 to power 256, and each slot represents 32 bytes of data. As smart contract state variables are different types like elementary types, array types, which is fixed or dynamic arrays, some user-defined types, and lastly, we have mapping data structures. The elementary types contain regular variables like simple we use in our source code programming, like integer type, string type, byte type variable. Arrays, we have fixed or dynamic. Fixed size, the fixed arrays, we know the size of arrays at the compile time, but for dynamic, we initiate the size of array at the runtime. Then we user define, and then we have mapping structure, which are hash mappings whose values distributed in the storage tray non-sequentially. And the placement of these state variables in storage tray is as they define in the smart contracts. We have example of short example of a smart contracts in which some state variables are defined. We have first variable A, which is an elementary type, and it holds the 0 slot on the storage tray. Next, we have a B, which is fixed type array of 2 elements. So it holds the next 2 storage tray slots. Next, we have C, which is a dynamic array, as we do not know the size of array at compile time. So it just assign a single slot. And the rest of the array gets slots when it's size declared. Next, we have a user-defined structure whose contain 2 regular variables. So it takes the next 4th and 5th slides slot of the storage tray. And lastly, we have a mapping structure E, whose has slot 6. So for extracting the storage of smart contracts, we need to extract the each value of these state variables. As all other regular variables are easily extractable, as we know their slots and we know get the values from the respective slots easily without any concern. But here we major challenge and major concern of state variable is the mapping structure, which we cannot easily extractable from their slot. So here, the challenging part of smart contract storage extraction is the mapping structure. The mapping structure is a key value structure in which by given the key, the value will be stored or get. As for storing the value against a key, The EVM of Ethereum cryptocurrency takes the slot number, which we assign the mapping structure. In the last example, we see which is a 6 slot, and hash hash this slot number with the key provided of the mapping structure, and the value stored to that respective hash address. So for getting the value of mapping data structure, we need to get all the keys of the mapping variable, because we have the hash, but as we know, hash is not reversible. We can't reverse it and get the key and then get the value. So main challenging part is that these keys also does not store in on the Ethereum blockchain. We cannot just go the Ethereum blockchains or transactions and get the list of keys of the Ethereum of smart contracts and extract the mapping structure. So for extracting the complete storage of smart contract, we need to get list of all get all the list of keys against all the mapping structures. So here's the transfers provide quite authentic and easy solution for getting the mapping keys and extracting complete storage of smart contracts. So if we get this storage, then one can easily move on to the migrate option or upgrade into a new smart contract without any concern. We just get the storage, get the data, user data of smart contract, and simply upgrade into the new one without any concerns. So for getting the keys of mapping variable, transfer perform the static analysis on the smart contract source code and approximate the mapping keys by using the key approximation algorithm. Here we have a key approximation algorithm. In this algorithm, it performs the reaching definition analysis and backtrace the definitions of all the mapping variables and identify their keys origins. Identify how the mapping variables get the keys from which source. So the key pass on to the mapping variable is from maybe from function argument that calls at the transaction time, or the value placed as an hard-coded value, or the some other mapping, some other state variable gives the value as a key to the mapping structure. So by identifying the origin, getting these perform static analysis and identifying the origin of each keys of the mapping variables, and move on to the extraction process for extracting the complete state of smart contracts. So for extracting the data, first we had the one we need slot numbers. So in instructions, it get the information of slot from a slot calculation algorithm and extract the regular state variables. But for mapping variables, it also needs the key approximation analysis results that provides information which mapping variables from where get the keys. So for simple hard-coded and state variable values, it easily extract the keys, but for the function argumented keys, originated keys, we need the transactions where these function calls and the keys provide keys passed on as a parameter. So it extracted the transactions of the smart contracts and analyzing it and get the list of the functions that calls, and then extracted the key, their arguments. And from arguments, we get the keys, and we can simply then hash with their slot numbers and get the respective values of the mapping variables. So once we get it, the complete storage of a smart contract, then we can easily upgrade into a new one. So for upgrading the smart contracts, we also need to check the data structure of the new smart contracts with the previous one. Is the new deployed smart contract has same data structure, same state variables as the older one? So for doing this, it get the upgrade process, get the data structure of the old one and the new one and the match on, and then the match variables data provided in their constructor, which can easily then deployed on the Ethereum blockchain, and we can get the benefits of new logic, new data structure with the old contracts. So that's the complete workflow of a transfer technology, this in which get the smart contract source code. It performs the slot calculation analysis and the key approximation for mapping slots analysis, and combine the both results in the extraction process, in which it also get the transactions for argumented origins mapping, argumented origin mapping keys, and then finally we get their complete state, which we in the upgrade process check the structures with the new contracts and then simply provide over your new upgraded smart contracts. So for checking our key approximation algorithm, we also perform results. We also check the approximation by getting the 47,000 smart contract data sets from different resources, and then perform the key approximation algorithm. Then by performing, we successfully run on 34,609 smart contracts. These are some little key approximation results from our data sets, in which we have the number of we have the smart contracts that include the mapping structure in the state variable is 24,731. And from which we total functions 1,24,000 analyzed, and we get the 1,84,000 originated mapping variable keys, which further classified in their arguments as they come from the function parameters or the hard-coded values or the state variables, or we have some runtime keys which we cannot extract it as they define on the runtime, or there's some limitations that we cannot detect it, so maybe miss out some key variables, but we are 0.9%, so it does not affect in most of the time. For guarantees over extraction procedures, we also proved that our key approximation algorithm is sound and precise. So as for measuring the soundness, we have 4 measures, which is true positive, true negative, false positive, and false negative. The true positive shows the keys of the mapping variables that actually exist in smart contracts, and algorithm key approximation algorithm also identified it. For true negative, which tells that the key does not exist, but the algorithm also does not identify it. Then we have next measure, it is false positive, which tells that the key actually does not exist, but the algorithm says that it exists and it identified it. And lastly, we have false negative, which tells that there is actually a key exists, but the algorithm does not report it. So for sound algorithm and for 100% extraction of storage of smart contracts, we may have false positive, which means we actually detect some keys which are not the part of the smart contracts, but we does not contain any false negative, which means that we actually does not report, we does not actually miss any key. If we miss any key, then we miss some part of the smart contract storage and we cannot completely extractable, and we miss these things. So we say that okay, our algorithm, key approximation algorithm is sound, which small table shows that the our data set which we run, we have 0 false negative, and with some false positive we extra detect something, but it does not hurt us. As we know, when Ethereum smart contract is deployed on Ethereum blockchain, then the assigned storage drive is initially empty. So if some key does not exist, then at the place of the storage try, we get the zero value. So simply from which keys we get the zero value, we simply discard it and get the actual the storage of the smart contracts. So here's we precise that in 99.9% cases, this transfer is completely extract the smart contract storage. So we have some future directions which on which we able to make more refined and more automatic cross migrations, cover more cross migration scenarios in which we give options to users that we simply get your smart contract data and deploy it on and migrate on any other platform other than Ethereum or Binance, Arbitrum, different blockchain platforms, and also improve the our upgrading prototypes. Some limitations will also improve it and provide the complete set of for users for migrating and upgrading the smart contracts with their complete storage without any concern. So next we have a small demo of the transfer project. Here, the small prototype we designed for giving the user and scene for the users for analyzing and extracting their smart contract storage. So here we run a small example. We take a smart contract into a set. For extracting the smart contract storage, we have the smart contract name, its address, and their source code. So we have these three requirements for extracting and analyzing the smart contract storage. So we get the name, address, and source code, and then we perform the analysis or key approximation analysis on the smart contracts, which tell us that is the mapping variables keys is extractable or not. So here's the results analysis results which tell that this smart contract is
Maha, sorry to disturb you, but the screen is not sharing. I think आपने जो just वो PowerPoint को share किया हुआ है, आपका demo नहीं show हो रहा.
Okay, wait 1 second. Sorry for the inconvenience. I again start the demo. Here's a small prototype for the transfer that provides the basic user and for users to analyzing and extracting their smart contract storage. So for this, we have three requirements in which we require the smart contract name, their address, and the source code. So here we run a small example in which we take a smart contracts of name into a set, which we have address and a small source code provide. So by fulfilling these requirements, we perform the analysis, key approximation analysis, which tells that the mapping variables of the smart contract is extractable or not. So here is our analysis results, which tells that our smart contract is 100% extractable, and this it have two mapping variables allowed and balances, and we can extract their keys and their mappings and the complete storage for the smart contracts. So next, we perform the extraction process. The extraction process, as I defined, it uses slot calculation algorithms results and key approximation algorithm results, and finally gives the complete storage for smart contract. So here's the extraction results, which we have a complete state variable list of smart contracts, and it gives the values with variables, and also for the mapping variables it provided the extracted keys with their corresponding values. So it has the complete extracted storage of smart contracts. Next, we also have the option that we can give your this storage data in the simple JSON form. You can use simply this data into any other platform or into any other way you want. So we provide the JSON format of this extracted data in a Next, we also have the option of for the upgrade, in which we upgrade your old contract data into your new contract one. So for upgrading, it requires your new data, which change logic or data structure. So here's we provided the new changed data structure source code of new smart contract. We can also provide the facility to, if you want to make some changes in this notepad, perform changes, and then we can move on to the upgrade process. By clicking the upgrade, it gives you the simple node file in which we have upgraded source code with the old smart contract data, which you can easily deploy on the Ethereum blockchain and get the benefits of old data with the new logic or data structures. Thank you.
Thank you very much, Maha, for the wonderful demo of Transfer. Transfer is something that we all are really excited about at Blockchain Security Lab, because this is not only a research and development project for us, but we are also looking forward to commercialize it as early as we can. So thank you very much, Maha, once again for being here with us for this wonderful demo. And now we do have our next speaker, Mr. Sayaf Haider, with us, who will be starting his presentation just in a couple of minutes. So meanwhile, I do have few announcements to make. After this session of Mr. Sayaf Haider, we will be having a break for half an hour. And after that, our valuable guest speaker, Mr. Mubashir Rahmani, will be joining us all the way from Ireland. So don't miss that session. It will be a very valuable session starting after a break of half an hour. So within that break, you guys can just mute your mics and turn off your cameras and can rejoin after the break. And that's it. So yes. Okay, so I guess we don't have any questions in the chat box for Maha. Awesome. Right, so I guess we should now start with the presentation of Mr. Sayaf Haider. Sayaf, I hope you can hear us, and I would also like to check.
Yes, I can hear you.
Awesome, so we can hear you as well. Awesome, so over to you, Sayaf.
Thank you. Assalamu alaikum, everyone. Today, we are going to present use cases of SDX in blockchain. For that, Asim is here with me to explain a little bit more about the scope. And then I will be share how we implement it in the real scenario. So first, Asim, can you please give us an intro about that so that we can move forward?
Okay, Sayaf, can you hear me?
Yes, I can hear you. Thank you, Asim.
Okay, thank you for introduction. Let me share my slide. Here it is. So, Sayaf, can you see my slide?
Yes, we can.
Yes, I can see.
Okay, so let's start then. Okay, so as Sayaf said that this talk is about the use cases of Intel SGX in blockchain. Probably the word Intel SGX is new for most of you. Intel SGX is basically a processor with security related extensions. And we will cover that aspect of security also. And we'll see that how this type of a security can help out to increase the trust in the blockchain. So I will first, in this talk, I'll first discuss the basics of the blockchain in the SGX, and then I'll go through the use cases of the SGX. And after that, we'll also, lastly, Sayaf will present a demonstration on application execution in Enclave. So you've heard too much about blockchain, so I'll just cover up quickly that blockchain enables decentralized append-only ledger. If you just see the figure here, if you see this figure here, you will see a big blocks. These are actually a major nodes, and these major nodes maintain ledgers, which is a replicated ledger. And if somebody wants to add a data into ledger, then consensus happens, and one of the major node is selected, which can append into ledger. And this is only append only. These major nodes can append only, cannot overwrite or cannot delete any transaction from the blockchain. So majorly this talk is about the security issue. So I want to just highlight a specific issue related to blockchain. So this issue is that I told you that major nodes are actually a major component of the blockchain. So these major nodes can be malicious. Even if the owner is not malicious, then there is another probability that owner have misconfigured the major node. There's a very high probability in this type of decentralized network, because anyone can join this network. You and me, if want to join a blockchain network, we need to just download an application and run over our computer. We will be connected with that block network. But who will ensure that I have rightly configured it? I am aware about all security standards. Nobody can ensure that. If you just see the conventional computing model, application runs over a large computing base, which includes operating system. And operating system consists of millions of million lines, which cannot be verified 100%. So these there is always a vulnerability in operating system, and CVE website report those vulnerabilities every year. So these vulnerabilities can be hacked, can be exploited by the attacker, and which leads to the take control of this most privileged layer in the computing model. And this layer can modify the application behavior and can launch the attacks like long range attack and the de-anonymization based attacks. So this operating system is not, this computing base is not limited to operating system only. There's also virtual monitors, which we usually say hypervisors, and also BIOS, and then system management mode. These are much things, but I'm just showing here a operating system which is very commonly known by everyone. So the problem is that that the trusting computing base app needs to for example, Ethereum app needs to trust on each layer in the computing model, on operating system, on processor, on hypervisor, everywhere. So to avoid this, that to reduce this trusted computing base, Intel SGX can be used. So before going toward the use cases, I'll just discuss the basics about the SGX so that you can understand when I'll discuss the use case. In Intel SGX, it's basically an extension to Intel processor. It's a hardware extension. It's a hardware extension to provide the confidentiality and integrity to security sensitive computation over privileged software, which may be malicious, which is operating system hypervisor and these type of things. So how this enables actually the SGX lets the app to rely only on processor. So to understand just this statement, we need to understand these 4 features of the CPU. I will just discuss these 4 features in detail in next slides. Let's discuss one by one. First one is that the SGX provides a protected memory. How? Let's see, usually in conventionally, where there is no SGX, a user space consists of application data, application code, and OS. And OS can modify application code and application data. But in SGX, there is another type of space called enclave. In this space is protected by the CPU. What this means? It means that if operating system wants to read or write to this space, then processor will directly reject that, will silently kill that request. So that operating system, even operating system, which is a privileged software, cannot be able to access the enclave. This is a bit, you can say, comparative to the conventional computing system. This is a change of privilege. Now a CPU is more privileged than anything. So this ensures the integrity and confidentiality of your code data loaded in an enclave. Even the operating system is malicious, even the operating system hacked by some attacker. So the second feature that SGX give is that it basically programs integrity check by the CPU. What it means? It means that when the program application first time loads into the enclave, CPU computes hash of the enclave. And that hash is used as a measurement hash for the next load. Obviously, this whole process, when first time when this hash calculated, at that time a strict supervision is required to create that, because this is a hash which will be used for the next loads. So when next time the application load into enclave, a hash is again computed, and CPU will compute that hash and compare it with the measurement hash which was calculated in the supervisor. So if that hash is equal, then the CPU will allow this application to run in enclave. Otherwise, it will not let the application to execute. So what it means? It basically means it ensures that always the expected code will be executed in the enclave, or you can say that the original code can be executed in the enclave. In other words, you can say that what the developer has developed, only that code will. Modified code or malicious code cannot able to run in enclave. But the condition is that at the first time when hash is calculated on the CPU, it should be calculated in a strict supervision. Okay. The third feature that Intel SGX added in the hardware is the addition of memory encryption engine in the CPU chip. So it looks like somewhat like this, the memory encryption engine here. And this memory encryption engine encrypts the data which belongs to the enclave when it goes out of the chip, and will not encrypt the data when it goes to the non-enclave memory space. This ensures that the data when it goes out from the chip is encrypted. So if someone launched some physical attack, sniffing of buses through oscilloscope or some other equipment, or tries to launch a cold boot attack on RAM or disk, he will get an encrypted data. So which is basically encrypted by the processor chip, not by the operating system, by the processor chip. So it means that OS also do not know the CPU key. So does not know the CPU key. So in this case, this ensures the confidentiality that processor, the data the data out from the chip is encrypted from the processor chip. So these are the sorry. Then the last feature is the remote attestation. In remote attestation, this is an interesting feature that Intel SGX provides an ensurety to a remote user that the application running in the enclave is the original code and it's running in the enclave. How this can happen? Actually, I just in previous slides I told you that the measurement hash is computed in a strict supervision. So that measurement hash is basically signed by the Intel, and that sign is the guarantee that it's running in the enclave and it's basically executing the right code, because a hash is basically indicating the right code. So this hash, signed hash, is given to the remote user to verify. So this is how basically in this model, or this data owner, the person who is remotely wants to access the computer just needs to trust on software developer like Ethereum, who does Ethereum, and also the manufacturer Intel. The owner of the structure needs not to trust, because this owner can be anyone. So this type of remote attestation is very helpful in blockchain most of the cases. So this ensures that the original code is executing in enclave to the remote user. Okay, so we have just I review the points related to SGX. So SGX does not allow the privileged software to access the enclave region, and also it creates some measurement hash which is used to measure the originality, the original code to run in an enclave, and then memory encryption engine which encrypts the data so that any other component, operating system or malicious privileged software cannot able to get information. It gets an encrypted data. And the last thing is the remote attestation, that remotely it can be ensured that the right code is executing in the enclave. So these are the 4 features which Intel XAS have given. And now we'll discuss the use cases of SGX. SGX can be used in sharded blockchain for the security reasons. Sharded is basically a difficult word, but it means partitioned blockchain. If you see the figure here, A, B, and C are the 3 partitions. So it partitioned the blockchain into multiple blockchains. And there is some inter and intra mechanism. We don't need to discuss that here. What I want to discuss here is that the assignment to these, a major node assignment to these partition is critical, because if all attacker, we allow every worker, every major node to join a partition with their own will, then all attackers will want to go into same partition and can launch a 51% attack. So this type of a thing is very dangerous in a blockchain. So secure assignment is required. Researchers said that instead of own will should be joined randomly. Means there is some random algorithm which decides that the new major node goes to which partition. So that random number generator can solve this problem, but a new issue came up, is this, that how to ensure that in these distributed environment that the random number generator, everyone who's joining is running in a right way, they're not biasing, they're not changing the seed or something like that. So how to ensure this thing? So SGX can be leveraged to ensure this. How? we just learned about the remote attestation. These already joined member will do a remote attestation with the new incoming major node, and they attest that that the incoming node have executed the right code in the enclave. If they have right code, right random number generator in the enclave, then he can join. Otherwise, he cannot join. So in this way, the insurity can be increased. Insurity can be happen through SGX. So another use case of SGX is to execute a private smart contract on a public blockchain like Ethereum. So, for example, why private smart contract need to execute? And there were some smart contracts like government tenders in that till the deadline, bidding the sellers who quote need not to be open. After that deadline, the scenario changes, but before deadline. So there needs a privacy till deadline. So the smart contract, such type of a smart contracts like a tender, government tendering, and these type of things needs a privacy while after for some time, and that privacy can be achieved through this SGX model. That SGX model, and this Shadow ETH presented one of that infrastructure. That what he said is that he said that this contract, the developer of the contract should deploy that contract in the enclave in the first time and refer this contract in a native Ethereum contract, which was called by the paper bounty contract. This bounty contract will be used to invoke the execution of this smart contract. This is off-chain execution actually. So this the person who wants to use this contract, or for example bid on this contract in tender system, so user will access this bounty contract, which is visible to everyone on Ethereum network, and this bounty contract then invoke the private contract in the enclave, where it will execute and the results will return. So in this way, a private contract which needs privacy, so the worker node, the operating system, malicious operating system even cannot able to extract the information of bits while execution, because it's in enclave and it's restricted, as I told in the previous slides. And the last use case in this presentation is related to de-anonymization attacks. In cryptocurrency, there is a concept of lightweight clients, which basically shares an address with the major nodes, and for verification of transaction, they share the addresses. Addresses is again, it's a pseudo-anonymous, but the thing is that there's some researchers have shown that through the graph study, and even you have heard one talk on machine learning based on that, the de-anonymization can happen. But those attacks are weak attacks, not too strong to claim that. But if we want to eliminate even those weak attacks, we can use SGX. And how SGX can help out, that these lightweight attest in the major node, these are the major nodes and these are the lightweight nodes, attest that that is the major node is executing in enclave, and give their encrypted address to the enclave, and enclave then search the data and gives the Merkle path back to the lightweight clients. And what's the security perspective in this is that the encrypted data goes into the enclave, and in enclave it's decrypted. So the malicious operating system or the owner of the major node will have no information, because he cannot read the enclave. So within the enclave, the things are going decrypted. So this is how the major node will not have information. This same scenario can be applied to the exchanges. For example, in Binance, usually people give their information, and Binance gives a key which is used in a blockchain. So there is a relation of name and key in there. So their that de-anonymization attack can be occurred easily on Binance, because there is already attachment there. If that exchange hacked, then everything will be visible on the blockchain, that what transactions you are doing. So the SGX can help out there also. So this is all about the use cases. Now I see Sayof to present a demo on the application. Thank you.
Assalamu alaikum again, and thank you so much, Hasim, for this brilliant presentation about the SGX and the use cases. So just give me a second to share it again on our side. So can you see my screen?
Yes.
Perfect. So now I'm going to present how should we execute application in SGX environment. Before moving forward, there are few requirements, or you can say the prerequisite for the SGX, and that includes the Intel microprocessor, which is not older than 6th generation. Secondly, it will be greater or prefer to use latest version of kernel 5.11 or higher. And if you are using the older one, you should use FSD based patches to work better. And this also preferable to use Ubuntu 18.04 or 20.04 to avoid compatibility issues while executing applications like Graphene. To understand SGX better, SGX is primarily divided into two parts, like the SGX PSW, which means Platform as a Software, and SGX SDK Software Development Kit. While there are also other two parts, as I mentioned, like AESM and Graphene, which you can say is also important, but there is a correlation with the first two. So don't worry, we will discuss shortly. So starting from the first one, as I mentioned, there are basically two parts. From those, PSW is the key one. It includes a set of drivers and dynamic link library. As Asim mentioned previously in the presentation, that SGX actually includes the changes in the hardware architecture. So there must be a drivers or dynamic link libraries which should support the PSW. SGX. So for that, PSW comes into account. So how it works is like the hardware enabler in BIOS setting is also supported by this part. While on Linux, the PSW functionality is implemented in the form of single binary called AESM service, which will be discussed shortly. So primarily there are three major parts. The first one, the launch service. So from the launch service, there is like enablement in BIOS setting. Then there is a EPID based attestation service, and the third one is like the algorithm agnostic attestation service. So to explain SDK, as we know, SGX Enclave is actually an implementation of a trusted execution environment that is much like an independent operating system instance. Here SDK comes into account. So in order to functionally useful, there has to be a way for the untrusted component of an application to access that trusted enclave functionality. And for the enclave request, certain operating system resources to request to the untrusted component of the application works. This is where SDK fits, and further applications like Graphenes come into the baseline of this part. So you need to install these two major components to enable SGX Intel in your testing bench. So as I mentioned, there are two other parts include AESM. So AESM stands Application Enclave Service Manager, which is actually a part of SGX platform software. But for Linux operating system, AESM run as a daemon process called AESMD. When the system starts, AESMD provides an untrusted API to communicate with architectural enclaves using a domain socket, whose path is hard-coded. All the messages transmitted between the architecture and application enclave will go through this path, the AESM, via the socket, and then it processed accordingly. Now come to the application layer. So Graphene is actually the application that we are using to support SGX. And why we are using this? Because it makes the usage of SGX bit easier, as they are like a lot of integrated libraries supported by that. So Graphene is basically a lightweight library operating system designed to run a single application with like a minimum host requirement. So it bridges the CPU to the unmodified execution mode. So this will be a very helpful for us. So this is basically the specification of the test bench where we run and test the SGX environment to validate how it works. And for those who are unaware of this terminology, gives a better understanding. So the specification includes we are using the Intel Core i7 processor, which is the latest one, the 6th generation. The operating system that we are using is 20.04, and the kernel version is 5.11 with low latency. As I mentioned, that PSW involved the enabling SGX in the BIOS. So this is the screenshot that I take it from my system, that you should enable it from your BIOS setting. So this is a basic requirement to run SGX. So if you are going to run SGX, so first thing must enable SGX in the BIOS setting. And the second step is to select the size of SGX enclave in the BIOS, as shown in the screen. They are basically the three sizes available in the Intel 6th generation process. The first one is the 32 MB, then there is a 64 MB and 128 MB enclave size available. So you can select according to your need. To test SGX, we take a real example that we use in the blockchain network. So for that, we write a code that is like a random function generator. And then we use it with the help of Graphene and SGX and put that into the enclave. And then we use a command to compile that code. So you can see in the first, the upper portion there, the code, which we put it on. And the second portion, you can see how should we compile the code in the SGX Graphene environment. So to verify SGX running or not, there is like a command that we should use. Is the first portion you can see the result of how should we compile using the Graphene SGX, the random function generator, and you can see the result on the upper portion of the screen. And then there's like there's a checksum generated by the SGX in the generated file with an SGX extension. You can see the checksum in that file as well. And finally, to see the SGX status while it's running or not, there are few commands, like you can see it using the grep SGX or listing command to see whether the SGN enclave is up or not. So this is how you can see. While there's one more thing I would like to mention in our community in this demonstration is that there are not no proper monitoring solutions available till now. So this is a scope available for everyone who is want to work on the SGX platform. So you can design some tools who can monitor the performance and statistical results of the SGX enclave. They have one well, that I found from like 6 or 7 months of research, there is one only that provide the performance metrics. There are no specific dedicated monitoring software available to monitor SCA. So this is a huge potential, and if you are working on this main, I will love to help you or give you a demonstration how should we proceed forward. So thank you so much for listening, and if you have any question, please feel free to reach us directly or through the hosting team. So thank you so much.
Thank you very much, Mr. Sayaf and Mr. Asim, for the wonderful presentation. So we do have a question in chat box by one of our participants. He's asking, can we run Docker in Intel SGX? Sayaf, your mic is muted. Please unmute.
Sorry for that. Thank you for the question. Actually, for the Docker side and the hypervisor side, the SGX currently is not supporting that. You have to run on the main architecture.
Right. Awesome. So, dear participants, do you have any other questions? I guess no. So perfect. Thank you very much, Mr. Sayaf and Mr. Asim, for the wonderful presentation. If you or participants do have any other questions, so they can always reach us through the Blockchain Security Lab, or they can directly contact our speakers on the details they have provided. So now we do have a 30-minute break. And after that, we will be joined by Mr. Mubashir Hussain Rahmani, who is the most cited researcher of 2020. He's a very well celebrated researcher from Ireland, and he will be joining us online for a detailed session starting from 1:45. Right, so I would request you all to stay here and listen the valuable things that Mr. Rahmani do have to share with us. So till then, we are going for a break and looking forward to see you all back at 1:45 p.m. sharp. Thank you very much.
Hello, everyone. Is everyone's back? Also, am I audible?
Yes, Abdurrahim, you are audible, and we are being joined by our respected guest, Dr. Mubashir Rahmani. So he'll be shortly joining, and I hope he have joined.
Okay, let's just wait for 2 or 3 minutes more so everyone can join back.
Yeah, let's wait for a couple of minutes. Meanwhile, please check with Dr. Rahmani that his audio and video is working properly.
Okay.
Assalamu alaikum.
Walaikum assalam. How are you, sir?
I'm fine. I'm fine.
Perfect. Just let's just wait for 2 more minutes.
Sure.
Since it was namaz break.
Okay. So may I share my slides?
Yes, sure.
Okay. So are the slides visible?
Yes, they are. So we'll start at 1:48. Hafiz, I guess there's some problem on your end. Just checking if everyone can hear us, right?
Yes, we can.
Perfect. Then there must be some issue with Hafiz or Rahman's system, I guess. Okay, so while the participants are joining back, let's start with the basic introduction. Let me introduce myself first. So I am working as a product designer at ITU Blockchain Lab. And the projects you have seen so far, like Transfer, Proof Chain, PKI chains, are the ones that I am working on to make the interface design of these apps easy to understand for you guys, the developers, the enthusiasts, etc. Also, I'm the guy who has been sending you all the emails. So if there was any issue with the emails, I really apologize. So next will be the part where I will be welcoming our next guest speaker, that Dr. Mubashir Hussain Rahmani. And honestly, there is a lot to tell about him. So I'll try my best. So number one, he is a senior member at IEEE, and he got the award of highly cited researcher in 2020 in the Department of Computer Science. He is also working as an assistant lecturer at the Department of Computer Science in Munster Technological University at Ireland. And he is also a board member at IEEE Communication Surveys and Tutorials. And there's a lot more. Most importantly, he's been so generous to join us at such a short notice. And thank you so much for that, Dr. Mubashir. And I'll quickly hand over mic to you so you can share the work you are doing in this area. So over to you, Dr. Mubashir.
Thank you very much for inviting me and giving me the opportunity to present myself. So basically, today I'm going to talk about how we can use blockchain in communication systems, or how communication systems can get some benefit from the blockchain. So just to quickly setting up the context and background, you may already aware about different types of cryptocurrencies available in the market. And as you can see, I have mentioned the currency price back in May 21 of different cryptocurrencies like Bitcoin, Ethereum, Litecoin. And you can see there's a huge market capital on these cryptocurrencies. So these cryptocurrencies are there, and people are heavily investing on these cryptocurrencies. And basically these cryptocurrencies, whether it's Bitcoin or Ether, they are basically based on blockchain technology. And blockchain is basically a distributed ledger system. So we can define blockchain in a formal way that it's some sort of a database that keeps a record of every transaction. And the ledger is basically distributed across many machines. And we use different cryptographic algorithms, hashes, and there are some basic features of blockchain that make it unique. So blockchain in principle is a ledger. So a ledger is basically a book, or you can say a computer file where you record and store some information. There can be different types of ledgers: sales ledger, purchase ledger, general ledger, that have been used in our daily lives to record some information. So here you can see before the computer, the records were, even now in some places, records are saved manually in the registers. These records can be in the form of, transfer of land or transfer of, any sort of money or any other tangible or non-tangible items. All of these information are being recorded manually. And then when the computer arrives, these records are shifted to computer, and then people start saving these and managing these records over computer using different spreadsheets or word processing softwares. And then there were further improvements and proper database systems were managed. For example, Oracle and other types of database systems. So these in these database systems, records are saved on several computers but managed by a central entity. And in distributed database systems, there is a possibility of managing these database and records in a distributed manner. Then we have this blockchain. So in blockchain, records are saved on several computers. And the unique feature of blockchain is that there is no central entity to control all these records. So this is the unique feature that makes blockchain different from traditional database systems. Now here you can see this is some very basic information about blocks. So each blocks will have some information, including block number, hashing information, and the transactions. And then there's a link between previous block and the next block. And then all these blocks are linked together so that you have a complete detailed transactions and you have a complete track of information. Now, how we can differentiate between blockchain and these distributed ledger, or in principle blockchain? Basically, there are several differences. One of them is both of them have contain common records, and in database system, in many instances, there is no control by the data entry operator on the data itself. It's the central entity that approves the data to be stored. While in the case of distributed ledger system, there's no central entity, and the nodes have the full authority to control the data. Moreover, in database system, you can have a global view, while in distributed ledger system, again, you can have a global view, and both of them can also be distributed in nature. But the main feature that distinguish distributed ledger system from databases is how records are, how consensus is carried out. In database system, there is no notion of, we can say, consensus, while in distributed ledger system or in blockchain, we have this notion of consensus that make a blockchain different from the database system. Besides this, there are some other vital characteristics of blockchain system. For example, they are transparent, immutable, auditability is possible, decentralized in nature. And if we just classify blockchain systems, we can classify in public blockchain, private blockchain, and consortium blockchain. In a public blockchain system, we have a completely decentralized system, while on the other hand, when we talk about private blockchain, we have a completely centralized system, and in consortium blockchain, we have a partially centralized system. And blockchain is basically managed in the form of layers. You can easily understand the working of each layer. For example, in the hardware layer, we have the underlying hardware, including CPU, GPU, and other hardware. Then we have this data organization and topology layer, where we talk about hashing, cryptographic algorithms, and how data can be stored in the ledger itself. Then we have the network and operating system layer, where we talk about how blockchain will work, and how peer discovery will be possible, how routing will be carried out. And then we have the consensus layer, in which we have different consensus algorithm trying to make consensus among the blockchain nodes. And then we have the upper layers, where we have different types of applications and different types of smart contracts and compilers that run. So this was just the very quick introduction of blockchain, and I presume you all are aware of blockchain in much more depth. So I move my discussion to the communication networks. So we all use heavily different types of communication networks. So communication networks can be classified majorly into two types: wired networks or wireless networks. So in wired networks, basically we use some sort of medium, some sort of wires, whether it's a copper wire or fiber optic cable, for transporting our data from one place to another. While in wireless networks, we don't require any wire. Definitely there will be a medium, and that medium is electromagnetic waves. But in principle, we don't have any sort of wire, and we can use electromagnetic waves as a medium. And some of the famous wireless networks that we use are, for example, cellular networks, the mobile phone network that we use, Wi-Fi network that we use. We can also talk about satellite networks, optical networks, wireless sensor networks. So these are a few of the wireless networks that are in our daily use. Now, when we look at these wireless networks, they operate on certain sort of frequency bands. So as you can see, when we listen to the radio, whether it's AM radio or FM radio, we are using some sort of frequency bands, and our radio receiver try to receive signals of different frequency bands, and these frequency bands are on kilohertz and megahertz band. When we talk about mobile phone communication networks, then again these mobile phones are operating on different frequency bands. For example, 800 megahertz frequency band, or 1600 or 1800 megahertz band. And then when we talk about Bluetooth or Wi-Fi, they use signals of gigahertz band. So you can see these wireless standards or wireless communication systems, they use these frequency bands, and these frequency bands are basically wireless radio spectrum electromagnetic waves. So wireless spectrum band or frequencies, or these spectrum, all of these are the same basically. So these are natural resource, like other natural resources, like we have petrol, gas, and other natural resources. Similarly, this wireless radio spectrum is also a natural resource. So if you can see in this figure, this wireless radio spectrum ranges from a few kilohertz to megahertz, gigahertz, and terahertz. And we can classify this wireless radio spectrum into licensed and unlicensed band. Note that I'm just focusing on the electromagnetic waves portion of these radio spectrum, and I'm not talking about the other portions of the spectrum band, where you have X-rays, gamma rays, or other types of rays. So this radio spectrum can be divided into two parts: licensed band and unlicensed band. So licensed band is the one where we try to pay the fees and then use this radio spectrum to develop or to maintain our communication system. While unlicensed band is the one where we don't need to pay anything. For example, using Wi-Fi network, we can simply connect to laptops without paying a single penny. So, and we can use Bluetooth or cordless phone or NFC devices or Wi-Fi or garage door openers. Also, all of these are using ISM band. So this wireless radio spectrum is when it's on the license band, it's very precious. It's very costly. For instance, Germany raised 6.55 billion euros for the auction of 5G mobile spectrum, and they were just selling out, auctioning 420 megahertz of the spectrum block. So you can imagine how much precious a small chunk of this radio spectrum is. So this radio spectrum, this is the license band, is basically has been assigned to different communication network in a fixed manner. In a fixed manner. So there's a static assignment of this wireless radio spectrum. So this radio spectrum, as you can see, this is the wireless radio spectrum map of United States, and it starts from few kilohertz and goes to megahertz. And you can see these different colors basically mention the use of these wireless radio spectrum band for different technologies. For example, you can see here this portion of the spectrum band is used for AM radio broadcasting purpose, and then this portion of the spectrum band is used for broadcasting television, and then later on different colors indicate different use of this radio spectrum. For example, satellite communication, a mobile phone communication, or Wi-Fi. So you can see by looking at this frequency allocation chart, the spectrum is allocated statically. It means that the one portion of the spectrum is used for AM radio and it is fixed. Not anyone else can use that portion of the spectrum. Or in simple terms, when they made the auction of this part of the spectrum, they assign it to any company, and that company is paying price to use that spectrum, and that company doesn't allow any other companies to use the same spectrum. So this is not just limited to United States. You can take the example of any country, and you will see that the regulatory body in that particular country is basically assigning the spectrum statically. For example, here I'm mentioning Ofcom, the United States regulatory body for telecommunication. So basically, they have this also the spectrum map or static allocation of frequencies. You can see different colors indicate different use of these spectrum band. For example, one can use a different spectrum for amateur or for satellite communication or for maritime or for aeronautical purposes. Similarly, when we look at Ireland also have this wireless radio spectrum map, which is managed by Comrag. And again, they assign the spectrum statically, and this spectrum is assigned to different companies in a static manner. In case of Pakistan, we have this Pakistan Telecommunication Authority, which is responsible for managing all the spectrum. So it is the PTA that basically regulates the spectrum. And when new companies, telecommunication companies, or any radio companies wants to establish their network, they contact PTA, and then they try to get license and try to buy a chunk of the portion of wireless radio spectrum. So it's the PTA who try to manage all the wireless radio spectrum in the context of Pakistan. If, for example, Mobilink or Ufone bought some portion of the spectrum from PTA, then PTA will be observing nobody else is using that portion of the spectrum that PTA has assigned to these companies. And if someone is trying to use that portion of the spectrum, PTA take serious actions. So the bottom line is that the current allocation of the wireless radio spectrum is basically has been done in a static manner. Means you assign the wireless radio spectrum to the companies statically. Now, when we look at the behavior of this wireless radio spectrum, so you can see in this graph on the x-axis, I'm mentioning different types of different frequencies, from lower frequencies to higher frequencies, when we go from kilohertz, megahertz, gigahertz to terahertz. And let's talk about how this wireless radio spectrum behave. So when you are at lower frequencies, the coverage area of your frequency will be very higher. So as you can see over here, this red bar indicates that the frequency, the coverage area of the frequency band in kilohertz can go up to 50s of kilometer. Means your signal can travel up to 50s of kilometer, 50 kilometer, 60 kilometer. So that's why you have the radio broadcasting stations very far, deployed very far. So and TV broadcasting station as well. So because their signal can travel to longer distances. But since we are at the lower frequency, they behave differently for other parameters. So let's focus on this coverage area. When we move to higher frequencies, let's say megahertz, the coverage area will reduce to 20 kilometers or 15 kilometers. And then we further go to higher frequencies, gigahertz, it further reduces. And when you are at terahertz frequencies, very higher frequencies, the coverage area reduces to few meters. So what are the examples for this? For example, you use Wi-Fi in gigahertz band. So your Wi-Fi signal can go up to 100 meters or 200 meters. And after that, the signal fades. And when you are using terahertz frequency band, even the signal cannot travel more than a few meters. And when you are at mobile phone, when you are using mobile communication network, your signal can travel up to 10 or 15 or 20 kilometers. So you can see the behavior of wireless radio spectrum from lower frequencies to higher frequencies is that in the context of coverage area, that as we go towards higher frequencies. And when we talk about the transmit power, which is indicated in blue color in this graph, we require higher transmit power for lower frequencies and less transmit power for higher frequencies, because the coverage area is higher and we require more energy to propagate the signal for longer distances. And the power consumption also behaves in the same manner. However, the bandwidth is totally opposite. At lower frequencies, since we are operating in kilohertz band, the bandwidth is very much lower. And as we go higher towards higher frequencies, the bandwidth is higher. So you can see this is the law, the principle made by the nature. Now, if your desire is to achieve higher bandwidth, okay, you need to go for higher frequencies. But the issue is that your signal, your coverage area will not be too much. So when you think about 6G or beyond 6G technologies, you want to operate on higher bandwidth. But the issue is that if you go terahertz frequencies, you need to deploy your base station or BTS even after a few meters, which is practically not possible. So there is a trade-off. So researchers and scientists are trying to focus how they can use higher frequency band to deploy the future communication networks. So again, they are looking for the higher frequency bands of megahertz and gigahertz to deploy 5G and 6G networks, and they are using some other techniques to optimize the performance of these wireless radio systems. So we need to keep this behavior of wireless radio spectrum in mind, and we can easily understand how this wireless radio spectrum works. So as I mentioned previously, this wireless radio spectrum is assigned in a static manner. So the problem is that when you assign the wireless radio spectrum in a static manner, there is some different use of spectrum in different portion or different days of the time. So FCC, Federal Communication Commission of US, conducted some experiments, and they saw that sometimes you can see here in this graph, sometimes the spectrum is heavily used, sometimes it is not used, sometimes it is intermittently used. So the reason for this use is due to the fixed spectrum assignment policy. And you have very limited available spectrum in today's wireless networks. So the result is basically inefficiency in the spectrum usage. And the result is in the creation of these holes in the wireless radio spectrum, which is also known as the white space. So the ideal thing is that we try to fill these gaps with this blue color. Means we try to efficiently utilize these inefficient use of wireless radio spectrum, and this can only be possible when we try to identify the use of the wireless radio spectrum at any particular geographical location or any time, and then we try to fill this gap. And this is only possible by using a technology which we called as cognitive radio network. So cognitive radio is basically a device, or you can say a laptop or mobile phone, which can change its transmitting and reception parameters dynamically, and it can react with the environmental parameters and change the configuration. So cognitive radio network, you can simply say that it's a device that can scan the wireless radio spectrum and see which portion of the wireless radio spectrum is in use or which portion is not in use. For example, when you are using a SIM, a connection of Mobilink or Uphone or any other telephone operator, basically you are using the license band, and you can only make a call on the frequency bands which Uphone or Mobilink has assigned to you. Now, when you are using cognitive radio instead of your Uphone SIM or Uphone or Mobilink SIM, basically you will have the same mobile phone, but what it will do, it will try to scan the whole wireless radio spectrum and see where the wireless radio spectrum is free. And as your mobile phone cognitive radio identify that free space, you can easily make a call. So it's some sort of a hacking mobile phone or hacking device. And this cognitive radio basically has been used heavily by the military. So in the army or in any army, in any country's army, we have a signal score. The signal score is responsible for communication requirements of the whole military. So this signal core heavily use this cognitive radio device. So when the military is deployed behind the enemy lines, they cannot use the physical infrastructure, telecommunication infrastructure of the enemy. So they need to have their own telecommunication infrastructure deployed instantly, and it should be reliable. So all of their communication network is basically based on these cognitive radio devices, and they are intelligent devices. And with these devices, the whole communication of the military can be possible between different soldiers, tanks, or aeroplanes, etc. So in this cognitive radio network, we have two types of users: primary users and the secondary users. Primary users are the licensed users, and the secondary users are unlicensed users. And the main responsibility of these cognitive radio devices is to identify the free spaces in the wireless radio spectrum and then start making communication. So there are four basic functionalities of these cognitive radio devices, including spectrum sensing, spectrum management, spectrum sharing, and mobility. So spectrum sensing means they identify the free space, and as soon as they find the free space in the wireless radio spectrum, they try to make a call or communication on that channel. Spectrum management means they try to identify the best channel, because channel can be of different qualities. So the best channel can be identified using the spectrum management cycle. Spectrum sharing means that not only itself, a cognitive radio device use the channel, but it can also share the information with other cognitive radio users as well. And finally, spectrum mobility means as soon as the primary user try to access the channel, they try to identify any other free channel and move to that channel. So this is how cognitive radio networks use the four basic cycles, cognitive cycles, to establish the network. So here in this figure, you can see on the left hand side, we have the primary network, which can be any licensed network. And on the right hand side, we have the cognitive radio network. So this cognitive radio network will basically can operate in two modes: with infrastructure or without infrastructure. With infrastructure, you will have a cognitive radio base station, which will be helping cognitive radio nodes to identify the free spectrum, and then they can establish the network over there. And in without infrastructure setting, cognitive radio nodes will cooperate with each other and will try to find the spectrum, the unused spectrum by themselves. So this radio spectrum has different sort of activities. It can be long activity. For example, when you use your mobile phone and have a free call package, you can call for longer times. So that type of activity of the channels will be called as long-term peer activity. And high peer activity, when you go to places which are very much congested, you can find a lot of people using the channels. So that will be some sort of high PR activity. PR means primary radio activity, the channel and the activity on the channels by the licensed users. And low PR activity means that you are in remote areas or you are using the channel or mobile phone in less peak hours. And intermittent means sometimes it is high, sometimes it is low, and it is short on and off periods. Now I move quickly to the main theme of my topic. So these cognitive radio devices can be used by the military, as well as in cases where we have different types of natural disasters. So when any natural disaster occurs, the telecommunication infrastructure get destroyed, and you don't have the BTS, you don't have any other thing. So besides the use of cognitive radio by military, we can also use it in natural disaster situation where we don't have any infrastructure possible. So for emergency communication, for public helping, we can use the cognitive radio devices as well. So the bottom line is that cognitive radio devices are those devices that use the wireless radio spectrum in a dynamic manner. They try to scan the channel and find which channels are free, and then try to establish a communication network over it. Now, as I mentioned, this wireless radio spectrum is basically is a very precious resource, natural resource, and the regulatory bodies, they try to auction it with very huge cost. In the case of Pakistan, PTA, again, the telecommunication companies buy this spectrum by paying a very huge amount of the cost, and then they can allow their users to use. Now this cognitive radio, when using the wireless radio spectrum, they can use it to manage it. For example, when we talk about this wireless spectrum management, this spectrum management, there are different parties involved in the management of this spectrum. For example, the regulatory body. In case of Pakistan, we have this PTA, Pakistan Telecommunication Authority, which manages this spectrum. And then we have this different companies which try to buy this spectrum. So in the case of a static scenario, they buy it once 5 year or once 10 year. But in the case of dynamic spectrum management, they will buy the wireless radio spectrum in a very short period of time. And the PTA or the regulatory body needs to manage this wireless radio spectrum and see which companies are buying and how to regulate this spectrum, how to share this spectrum, and above all, how to trade this spectrum. So there's a complete life cycle involved in the management of the wireless radio spectrum, ranging from the role of the spectrum regulator, and then it is assigned to different telecommunication companies, and then it is assigned to different users. And then with the help of this blockchain, we can even trade this spectrum in a dynamic manner. Right now, when we use the SIM of any telecommunication company, we can not allow anyone else to use that spectrum that we are using. But with the help of this cognitive radio and blockchain technology, the user, the mobile user, can facilitate any other users and buy and trade the spectrum on runtime. So, and this trading, this auction can be possible with the help of this blockchain technology in a very quick period of time. And smart contracts also can help to manage this spectrum trading, where you can automate the process of invoking different trading criteria or trading actions, and you can also develop new business models for the spectrum trading as well. Future trading can also be possible, that you may, for example, write a smart contract that if the price of the spectrum reaches to this point, just buy the spectrum or sell the spectrum. You can also reduce the business process time. Traditionally, when you try to buy the auction and you manage it with the regulatory body, it takes few days. But with the help of this blockchain technology, we can reduce the business process time, and one can buy very easily and quickly the spectrum. And above all, the system will be much more autonomous. And one of the main advantage that blockchain will bring to this sort of spectrum trading is that the spectrum trading for short period of times will be possible. And previously we were trading the spectrum for for years or for 5 years or 10 years, but with the help of this blockchain enabled spectrum trading, we can even go for wireless spectrum trading for in the case of months or weeks or days, or even it is possible to go for hours and minutes or even seconds. But definitely such type of system need to be developed. So this is about how we can use the blockchain technology for spectrum trading, or for the management of the spectrum, and for helping the cognitive radio devices to buy and sell the spectrum. So if you require some other information on this topic, I have mentioned it in these books, and there are some other references as well which are here, which you can also study, which talks about how different types of ledgers or different architectures of blockchain can be possible to enhance the performance of these wireless networks. So that's all from my side. If you have any question, most welcome.
Thank you so much, Dr. Vishal. I have a question, and I've already posted that. The trading you're talking about, is it like anyone that owns a device, that cognitive radio device, can participate in that trading?
So you can basically there is no standard developed right now. So once the standard develop, maybe when we go for consortium of telecom companies and those cognitive radio devices which will be the part of that consortium that can buy and sell the radio spectrum. But right now we can say that it depends upon which type of architecture, public architecture or consortium architecture we are going to design for such type of spectrum management. So I cannot say that it can be a public, totally public. It can be a consortium, but still it is in development stage and no standard has been developed.
Also, the fluctuating prices of all the cryptocurrencies right now, specifically the trend of NFTs, non-fungible tokens, have totally changed the trends of Ethereum prices. So how would that affect this trading process? Because we currently we cannot rely on the prices of cryptocurrencies, right? That they will be consistent.
So in the case of it's a very precious resource. So there need to be some interaction of the regulatory bodies in the system. We cannot just let it go alone. Like in the case of cryptocurrencies, there is no regulatory body like the government or the banks. So in the case of management of these wireless radio spectrum through blockchain, there need to be a role of a regulatory body, government. So what we are saying over here is that the regulatory body, instead of using the traditional database system, they will be using the blockchain system, and the blockchain system will facilitate in buying and selling of the spectrum. So the role of the regulatory body will be there. Yeah, so such cases of too much fluctuation will not occur because of the role of the regulatory body in this case.
Right. Actually, I'm very curious about this topic, so I'm asking multiple questions. Because for that, I guess, let's say if we talk about Pakistan, the government needs to first understand the importance of blockchain and the cryptocurrencies, then they can jump to this one. So the first step should be the acceptance of blockchain technology in the government level, right?
Yes.
Any questions?
So we have on the chat, there is a question that if PTA controls the spectrum in a country, would it allow individuals to interfere in the spectrum trading? Yes, definitely. PTA will be the regulatory body in case of Pakistan, and that blockchain system of a spectrum auction will be controlled and managed by the PTA. So they will, in principle, they should not interfere too much. So there should be some level of flexibility, or allowing individuals to buy and sell. That's how the system works. If too much interference will be there from the regulatory body, definitely the system will not work in longer terms. So the interference should be minimum, and interference should be in the cases where someone violates the rule of the blockchain system.
Right. I guess what Hatim was thinking, that, for example, we have the cases where the PTA turns off all the mobile connections in Muharram. So that's the point where it interferes the connectivity of the whole country, actually. So
yes, that is a different thing. Basically, if PTA just blocks the system, the telecommunication system, PTA cannot block the system of military. Military have their signals code, and they have their own communication system, and they basically use the cognitive radio devices. So cognitive radio devices is basically like, when you first time buy your television set, you tune and you start receiving signals of different frequency bands. So the television set is basically scanning a limited amount of channels. But in the case of cognitive radio, the cognitive radio has the capability to scan the whole spectrum from kilohertz, megahertz, gigahertz, and they can also send the signal as well. Okay, so when PTA blocks the communication system in Pakistan, what they do basically, they jam the signals generated by the BTS by different telecom companies, but they cannot jam the signals of cognitive radio devices until and unless they have the cognitive radio device itself.
right, there is another question.
Why would PTA want to give so big chunk of money to private individuals? Basically, this is a business model where when there is a competition, there is a prosperity, involvement of prosperity in the country. So if you talk about old days, there was only a single telecom company. So PTA allows multiple telecom companies to come and to establish their communication network. So when different companies come, you can see the price goes down, and everybody was using the telecommunication network. So going beyond this point, when you enable this sort of trading at very individual level, you will again increase the level of interaction by different parties, by different individuals in the communication network. It's like you have the electricity network in Pakistan, where WAPDA or different companies provide you the electricity. But then, government wants that each individual generates their own energy using renewable energy resources like solar panels on their rooftops or wind turbines at lower level. And then if they have generate some extra energy, they inject back that energy to the grid. And in this way, they can have a bill of zero amount, or even they can earn the money through injecting electricity to the grid. Similarly, when you invite people to involve at a very smaller level of these buying and selling of the spectrum, and using this spectrum auction, it will generate the revenue and it will bring prosperity. Any other question?
There's one from Zakaria. How can we incorporate cognitive communication for bushfire disaster?
So basically, there are two types of networks: wireless sensor networks and cognitive radio devices or cognitive radio network. Wireless sensor networks are sensors that can detect different types of fire incidents. So we can have such type of sensor devices to detect any natural disaster or any sort of fire incident. And cognitive radio is basically a communication network like we have mobile link or Uphone or any other satellite network. So cognitive radio can help you in post-disaster situation where you don't have the existing infrastructure. For example, an earthquake came and you have all the BTS towers and all the infrastructure goes not working. So you can bring your cognitive radio devices and establish a network instantly. This is how this is the use of cognitive radio basically.
So I guess that's the end of the Q&A. Does anyone have any questions? Or you can directly contact Dr. Mubashir. We will share his contact details in the email. So if anyone is interested to join him in his work, I guess Dr. Mubashir, you are working in this area and you are open to receive applications, right?
Yes, yes.
Perfect. So I guess that's the end of this day. Thank you so much, Dr. Mubashir Rahmani. It was a delight to have you on this workshop specifically at such a short notice. And I guess everyone enjoyed that. So that will be an end to this day. We will join you guys tomorrow, same time, 10 a.m. with some more guest speakers. Dr. Adnan Noor, he is the Dean of Computer Science at ITU, and he will be talking more on the networks side of the blockchain. Also, Dr. Taha Ali from NUST University would be joining us for a similar content. So thank you so much, guys. I guess that's wrap.
Thank you very much.
Also, if you're welcome, sir. Also, it would be nice if you could, all of you could turn on your cameras so we can have a group photo that can be published on the social media in like 2 minutes.
Do you want me to stay or I may leave?
Totally up to you, sir. We are just going to take a group picture. If you want to join, you're welcome.
Okay, so meanwhile, I would also like to take the opportunity to thank Dr. Mubashir Rahmani for joining us today. So Dr. Saab, I would like to thank you on behalf of Blockchain Security Lab. It was really nice listening to you, and we are hoping to invite you in some other session again. Thank you very much.
Thank you very much. Thank you very much.
Dr. Saab, can you please stop sharing the presentation so we can have the grid of the participants? Perfect. Okay, so let's start the screen recording. Thank you so much, everyone. Let's meet tomorrow.
Thank you.
Bye-bye.